Hello there, and welcome to Science for Sleep, where curiosity settles in, gets comfortable, and science takes its time instead of rushing ahead. Tonight, we're easing into something that might sound a little intimidating at first, but don't worry, we'll take it slowly. No sudden jumps, no overwhelming details, just a steady, gentle look at one of the most fascinating things in the universe. Black holes. Now, black holes tend to have a certain reputation. They're often described as cosmic monsters, devourers of stars, places where nothing escapes, not even light. It all sounds quite dramatic, almost like the universe decided to include a few villains just to keep things interesting. But as we'll discover together, they're not quite as chaotic or destructive as they seem at first glance. In fact, in many ways, they're surprisingly calm, quiet even, patient. And before we go any further, I'd like to ask you something simple. Where are you listening from right now? Maybe you're in bed, the lights off, just letting your thoughts slow down a little. Or perhaps you're somewhere else, wrapped in a blanket, watching the world dim around you. And what time is it where you are? Late evening? Early morning? One of those quiet in-between hours where everything feels just a bit softer? It's a funny thing, isn't it? We're about to talk about objects that can bend time itself, stretch it, slow it down. And yet here we are, checking the clock, noticing the hour, settling into our own little moment. Somewhere out there, far beyond what we can see, black holes are quietly shaping entire galaxies. And here, right now, you're simply listening. If you find this kind of journey relaxing or interesting or just a nice way to wind down after a long day, I'd really appreciate it if you gave the video a like and maybe subscribed. It helps this calm little corner reach more people who might need a moment like this too. Now, I should mention there's a small risk here. Not that anything will go wrong, of course, but that you might find this so intriguing that you stay awake a little longer than planned. If that happens, well, at least you'll have spent that time exploring the strangest objects in the universe. Not a bad trade. So, let's begin gently. When most people hear the words black hole, they imagine something dramatic. A swirling vortex maybe, pulling everything inward like water down a drain. Stars stretching into thin strands, planets vanishing instantly, light itself being swallowed whole. It's a powerful image, and not entirely wrong, but it can give the impression that black holes are constantly active, constantly consuming, constantly doing something. The reality is a bit quieter. A black hole at its simplest is a place where gravity has become incredibly strong. So strong, in fact, that once something gets too close, it can't escape anymore. Not because it's being aggressively pulled in at all times, but because the structure of space itself has changed in that region. It's less like a vacuum cleaner and more like a deep valley. If you're far away, everything feels normal. But if you wander too close to the edge, there comes a point where climbing back out becomes impossible. What's interesting is that most of the time, black holes just sit there. They don't actively hunt. They don't chase things down. If our sun were somehow replaced by a black hole of the same mass, Earth would keep orbiting almost exactly as it does now. Same distance, same path, same yearly cycle. The only difference would be, it would get very dark. That's one of the first surprises people encounter. Black holes aren't cosmic vacuum cleaners. They're more like quiet anchors in space, influencing their surroundings through gravity, but not dramatically pulling everything in unless it gets very close. Still, there are moments when black holes do become more noticeable. When gas, dust, or even entire stars drift too near, they can form what's called an accretion disk. That's a thin, glowing ring of material spiraling inward. And this is where things start to look more like what you might expect. The material heats up as it falls, sometimes reaching temperatures hotter than the surface of stars, glowing brightly before disappearing beyond the point of no return. But even then, it's not chaotic in the way we might imagine. It's more like a slow, steady process, a gradual inward journey. Not a sudden gulp, but a long spiraling descent. And that brings us to something quite important. Not all black holes are the same. In fact, they come in a wide range of sizes, and some of them are so extreme that even scientists have to pause for a moment and double-check their calculations. That's really what this whole journey is about. Not just black holes in general, but the most extreme ones we've ever found. The biggest, the brightest, the fastest, the strangest. Some of them are so massive that they outweigh billions of suns. Others formed incredibly early in the universe, appearing far sooner than we thought possible. A few seem to wander through space alone, without a galaxy to call home, and some spin so quickly that they drag space itself along with them. It's a bit like looking at mountains on Earth. At first you learn what a mountain is, a raised part of the land, shaped by geological processes, but then you start noticing the extremes. Everest, towering above everything else, deep valleys carved by glaciers, unusual formations that don't quite fit the pattern. Black holes are similar. Once you understand the basic idea, the real fascination comes from the exceptions, the ones that stretch the limits of what we thought was possible. But before we go there, it helps to get comfortable with the foundation. Imagine for a moment a very simple scenario. A star, much larger than our sun, living out its life over millions or even billions of years. It spends most of that time quietly fusing hydrogen into helium, releasing energy, shining steadily. From the outside it looks stable, predictable, reliable, but deep inside something is slowly changing. Stars exist in a balance. On one side, gravity is constantly trying to pull everything inward. On the other side, the energy from nuclear fusion pushes outward. As long as those two forces are in balance, the star remains stable. Eventually, though, the fuel begins to run out, and when that happens, the balance shifts. Without enough outward pressure to counteract gravity, the star begins to collapse inward. For smaller stars, this collapse stops at a certain point, forming dense objects like white dwarfs or neutron stars. But for the most massive stars, the collapse continues further. There's nothing left to stop it. Gravity keeps pulling inward, matter gets compressed more and more, and at some point the density becomes so extreme that the escape velocity exceeds the speed of light. That's the moment a black hole forms. It's not an explosion, at least not in the usual sense. It's more like a quiet transition. A star that once shone brightly becomes something invisible, detectable only by its effects on the surrounding space. And once it forms, it can remain there for a very long time, billions of years in many cases, just existing. Now you might be wondering, if black holes are invisible, how do we even know they're there? That's a very reasonable question. The answer is that we don't see black holes directly. Instead, we observe what they do. We watch how nearby stars move, how gas behaves, how light bends around certain regions. It's a bit like noticing the wind by watching the trees sway. You don't see the wind itself, but you can clearly see its effects. One of the earliest hints came from observing stars orbiting something that couldn't be seen. They were moving as if there were a massive object at the centre, but nothing visible was there. No light, no radiation, just empty space. Except it wasn't empty. It was a black hole. Over time, as our instruments improved, we found more and more of these objects. Some small, some enormous, some quietly sitting at the centres of galaxies, others actively feeding and glowing with incredible energy. And gradually the picture became clearer. Black holes aren't rare anomalies. They're a natural part of the universe. In fact, there are likely millions of them in our galaxy alone, most of them small, relatively quiet, drifting through space or orbiting other stars. But at the centres of galaxies, including our own, there are much larger ones. Supermassive black holes, containing millions or even billions of times the mass of our Sun. And those are where things start to get extreme. But before we fully step into that territory, it's worth pausing for just a moment. Because even though black holes are often described in dramatic terms, there's something almost calming about them when you look at them this way. They're not chaotic forces tearing through space at random. They follow rules, very precise rules, the same laws of physics that govern everything else. They don't rush, they don't panic, they simply exist, shaping the space around them in quiet, predictable ways. And maybe there's something reassuring in that. The idea that even the most extreme objects in the universe are still part of a larger order, a system that, while complex, is not entirely unpredictable. So as we continue, we'll start to explore the more unusual black holes, the ones that stand out even among their own kind, the ones that challenge our understanding, stretch our imagination, and occasionally make scientists pause and say, that shouldn't be possible, and yet, here it is. We'll move gradually from the ones closest to what we already understand to those that push the limits of what we thought could exist. And somewhere along the way, you might notice something interesting, that the universe, even at its most extreme, isn't just about violence or destruction. It's also about structure, about patterns, about quiet processes unfolding over immense stretches of time. Alright, let's take this a little further, gently building on where we left off, and spend some time with a simple question that turns out not to be so simple after all. What is a black hole, really? It's one of those phrases that gets used so often that it starts to feel familiar, almost ordinary. You hear it in documentaries, in movies, in casual conversations. It becomes part of the background, like galaxy or star. But if you pause for a moment and actually try to picture what a black hole is, things get a bit less clear. Because it's not quite an object in the way we're used to thinking about objects. You can't stand on it, you can't touch it, you can't even really see it, and yet it's very real. So let's approach it slowly, starting with something we do understand. Gravity. Gravity is the force that keeps your feet on the ground, the moon orbiting Earth, and Earth orbiting the sun. It's something we experience constantly, even if we don't always notice it. Drop something, and it falls. Jump, and you come back down. Everything with mass pulls on everything else. Now, normally gravity is fairly gentle. The Earth's gravity feels strong to us, but compared to the rest of the universe, it's actually quite modest. You can jump against it. A rocket can escape it. Light itself travels freely away from Earth without any trouble. But what if you took a lot of mass and packed it into a very small space? Gravity would become stronger. Pack it tighter, and it becomes stronger still. Keep going, compressing more and more mass into a smaller and smaller region, and eventually you reach a point where gravity becomes so strong that nothing can escape. Not a rocket, not a beam of light, not even the fastest thing in the universe. That point is what we call a black hole. So, in the simplest sense, a black hole is a region of space where gravity has become so intense that escape is no longer possible. Not because something is actively pulling you in like a vacuum cleaner, but because the very structure of space around it has changed in such a way that all paths lead inward. There's a boundary around this region, and it has a rather dramatic name, the event horizon. If you imagine standing at a safe distance outside the event horizon, everything behaves more or less normally. You could orbit the black hole, observe it, even send signals back and forth. But if you cross that boundary, there's no coming back. And what's interesting is that nothing special happens exactly at the edge itself. There's no sudden jolt, no visible line, no warning sign floating in space saying "do not enter." From your perspective, you might not even notice the exact moment you crossed it. But once you're inside, every possible path forward leads deeper in. It's a one-way direction, built into the geometry of space. Now that might sound a little abstract, so it helps to think of space not as empty, but as something that can bend and curve. Imagine placing a heavy ball on a stretched fabric. The fabric dips downward under the weight. If you roll a smaller ball nearby, it will curve inward. Not because something is pulling it sideways, but because the surface itself is curved. That's a common way to visualize gravity, and with a black hole, that dip becomes extremely steep. So steep that beyond a certain point, all paths lead downward no matter how you try to move. Even light, which normally travels in straight lines, ends up following that curve, and that's why black holes appear black. Not because they're made of something dark, but because light that gets too close simply can't escape to reach us. So, what we see instead is the absence of light, a kind of silhouette against the background of space. But here's where things get even more interesting. If you were watching someone approach a black hole from a safe distance, you wouldn't actually see them cross the event horizon. Instead, they would appear to slow down more and more as they got closer. Their movements would stretch out. Their signals would become weaker and more redshifted, fading away gradually. To you, it would look like they're frozen at the edge, never quite crossing. But from their perspective, they would pass the event horizon in a perfectly normal amount of time, continuing inward without noticing anything unusual at that exact moment. This difference in perspective is one of the strangest aspects of black holes. Time itself behaves differently near them. Closer to a black hole, time runs more slowly compared to regions farther away. Not just in a metaphorical sense, but literally. If you had two clocks, one near a black hole and one far away, the one near the black hole would tick more slowly. So, in a way, black holes don't just affect space, they affect time as well. And that leads to an idea that can feel a bit unsettling at first. A black hole is not just a place. It's a region where space and time are so distorted that the usual rules no longer apply in the way we expect. Now naturally this raises another question. What's at the centre? If everything falls inward, where does it go? According to our current understanding, all the mass of the black hole is concentrated into an extremely small point, often referred to as a singularity, a place where density becomes effectively infinite, and the known laws of physics break down. But it's important to say this carefully. We don't actually know what a singularity truly is. Our equations point to it, but they also stop working there. It's like reaching the edge of a map where the details fade out. We can describe what happens up to a certain point, but beyond that things become uncertain. So while the idea of an infinitely dense point is useful, it's probably not the full story. There's likely something deeper going on, something we don't yet fully understand, and that's part of what makes black holes so fascinating. They're not just objects we can study and categorize, they're also places where our current knowledge reaches its limits. Now, earlier, we talked about how black holes don't actively hunt things down, and that's worth reinforcing, because it's one of the biggest misconceptions. If you were far away from a black hole, and it had the same mass as the Sun, you could orbit it just as you orbit the Sun now. It wouldn't suddenly pull you in. You'd only be in danger if you got very close. And even then, the experience would depend on the size of the black hole. For smaller black holes, the gravitational difference between your head and your feet would be very large, stretching you out in a process sometimes called spaghettification. It's not the most comforting term, but it's quite descriptive. For larger black holes, especially the supermassive ones, that difference can be much smaller at the event horizon. In theory, you could cross it without immediately noticing extreme stretching. The journey inward would still be one way, but it might not feel dramatic at first. Again, not that we're planning any trips anytime soon, but it highlights how varied black holes can be. They're not all the same. Some are relatively small, just a few times the mass of the Sun. Others are enormous, containing millions or billions of solar masses, and as they grow larger, their behaviour changes in subtle but important ways, which brings us back to the bigger picture. When we say black hole, we're not talking about a single uniform thing. We're talking about a category of objects defined by a certain condition. Gravity strong enough that nothing can escape. Within that category, there's a wide range of possibilities, and some of those possibilities are quite extreme. There are black holes so massive that they dominate entire galaxies, others that formed very early in the universe, growing faster than we can easily explain, some that spin incredibly fast, dragging space along with them, and a few that seem to wander through space alone, without a clear origin. Each of them follows the same basic idea, but each expresses it in a different way. So how do you find something that doesn't emit light, doesn't reflect light, and can't be seen directly at all? It's a bit like trying to spot an invisible object in a dark room. You can't look for the object itself, so instead you look for what it does. You notice the way things around it move, the way they behave differently, the way something unseen seems to be influencing them. That's exactly how the first black holes were discovered. For a long time, black holes existed only as mathematical predictions, solutions to equations, interesting ideas discussed in physics, but not something anyone had clearly observed. Even Albert Einstein, whose work helped make black holes possible in theory, wasn't entirely convinced they would exist in reality. They seemed a bit too strange. And yet, the universe has a way of taking even the strangest ideas and quietly making them real. The turning point didn't come from looking for black holes directly. It came from studying stars, more specifically binary star systems where two stars orbit each other. These systems are quite common, two stars bound together by gravity circling around a shared centre. You can often observe both of them, tracking their motion, measuring their light, understanding how they interact. But sometimes something odd happens. You see one star, and something else that you can't see. The visible star moves as if it's orbiting a companion, but that companion doesn't emit any light. It doesn't show up in telescopes, it's just missing, and yet its presence is unmistakable, because gravity doesn't lie. If a star is orbiting something, that something has mass, and by carefully measuring the motion of the visible star, astronomers can estimate how massive the invisible companion must be. At first, this raised some interesting possibilities. Maybe it was a very dim star, maybe a neutron star, something incredibly dense but still detectable in certain ways, or perhaps just something we didn't fully understand yet. But in some cases, the numbers didn't add up. The unseen object was too massive to be a neutron star, too compact to be anything else we knew of. It wasn't emitting light, and yet it had the gravitational pull of several suns. There was only one explanation left: a black hole. One of the most famous early examples of this is a system known as Cygnus X1. The name itself sounds a bit technical, but the story behind it is quite human. It was discovered in the 1960s as a strong source of X-rays coming from the constellation Cygnus. Now, X-rays are a form of very energetic light, usually produced in extreme environments. So, when astronomers detect a strong X-ray source, it often means something unusual is happening. In this case, they found that the X-rays were coming from a binary system, one visible star and something else, something unseen. But here's the interesting part: the X-rays weren't coming from the star itself. They were coming from material around the invisible object. Gas from the visible star was being pulled toward this unseen companion, forming a swirling disk as it spiraled inward. And as that gas fell closer and closer, it heated up dramatically, reaching temperatures so high that it began to emit X-rays. So even though the black hole itself was invisible, the process of matter falling into it lit up the surrounding space. It's a bit like watching water swirl down a drain, not because you can see the drain itself, but because of the movement and energy of the water around it. By studying this system, astronomers were able to estimate the mass of the invisible object, and it was far too massive to be a neutron star. The simplest explanation, and the one that fit all the observations, was that it was a black hole. Cygnus X1 became one of the first strong candidates for a real black hole, and at the time, that was a big deal. Because it meant that black holes weren't just theoretical curiosities, they were actual objects in the universe, influencing real stars, producing observable effects. Still, scientists are cautious by nature. One example isn't enough. You want multiple observations, different systems, consistent evidence. And over time, more systems like this were found. Other X-ray sources, other binary systems, other cases where something invisible was exerting a powerful gravitational influence, each one adding to the picture, reinforcing the idea that black holes were not rare anomalies, but a natural outcome of stellar evolution. But even then, there was still a certain distance to it all. We were inferring the existence of black holes, deducing them from indirect evidence, seeing their effects, but not the objects themselves. It's a bit like hearing footsteps in another room. You know someone is there, even if you can't see them, and for a while, that was enough. But as technology improved, our ability to observe the universe became more refined. Telescopes became more sensitive, instruments more precise, and slowly the evidence became harder and harder to ignore. One of the most compelling pieces of evidence came from observing the centers of galaxies. Astronomers noticed that stars near the centers of certain galaxies were moving incredibly fast, much faster than they should be if only visible matter were present. In our own galaxy, the Milky Way, careful observations revealed stars orbiting an invisible point at tremendous speeds. By tracking their motion over years, even decades, scientists could calculate the mass of whatever was at the center, and once again, the numbers were staggering. Millions of times the mass of the Sun concentrated into a very small region. Too small, too dense, too massive to be anything other than a black hole. This wasn't a small stellar black hole like those formed from collapsing stars. This was something much larger, a supermassive black hole sitting quietly at the heart of the galaxy. And not just ours. It turns out that many galaxies, perhaps most of them, have these massive black holes at their centers, anchoring the galaxy, influencing the motion of stars, shaping the structure of the system over vast periods of time. So by this point the idea of black holes had shifted. They were no longer rare, hypothetical objects. They were common, fundamental, part of the architecture of the universe itself. And yet, for all this evidence, we still hadn't actually seen one. We had strong indirect proof, observations of motion, radiation, gravitational effects, but no direct image. Nothing you could point to and say, there it is. That would come later. But even before that moment, the case for black holes had become overwhelming. It's interesting to think about how much of science works this way. We often don't observe things directly at first. We infer them. We build models, test predictions, look for consistency. And gradually, as more pieces fall into place, our confidence grows. Black holes followed that path, from equations to possibilities, from possibilities to evidence, from evidence to acceptance. And all the while they were there, quietly existing, shaping their surroundings, waiting to be noticed. There's something almost gentle about that. No dramatic announcement, no sudden reveal, just a slow accumulation of clues, leading us to a deeper understanding of what was already there. What kind of star becomes a black hole? How massive does it need to be? What happens in those final moments before collapse? Let's slow things down for a moment and stay with that idea we ended on. A star shining quietly in the distance, going about its life in a way that feels steady and predictable. Because for most of its existence, a star really is stable. It wakes up, in a sense, not with a sudden beginning, but with a gradual gathering of gas and dust. Gravity pulls material together, the pressure builds, temperatures rise, and eventually, deep in its core, something important begins. Fusion. Hydrogen atoms start combining into helium, releasing energy in the process. That energy pushes outward, balancing the inward pull of gravity. And as long as that balance holds, the star lives a calm, steady life. It shines. It warms its surroundings. It exists in that delicate equilibrium for millions, sometimes billions of years. And if you were watching from far away, nothing about it would seem dramatic. No sudden changes, no obvious signs that anything unusual is coming. Just a quiet point of light in the sky. But inside, very slowly, something is changing. The fuel is being used. Hydrogen, the simplest and most abundant element, doesn't last forever. Over time, the core fills with helium, and the fusion process begins to shift. The star adjusts, finds new ways to maintain balance, sometimes expanding, sometimes becoming brighter. Still, the pattern holds. Gravity pulling inward, energy pushing outward, until one day the balance starts to fail. Now, the way this happens depends a lot on the size of the star. For smaller stars like our Sun, the ending is relatively gentle. The outer layers drift away, forming a soft, glowing cloud called a planetary nebula. The core remains behind as a white dwarf, dense and slowly cooling. But for much larger stars, the story is very different, and this is where things begin to change in a more dramatic way. Massive stars burn through their fuel much more quickly. They live fast, shine brightly, and use up their resources in a fraction of the time. As the core evolves, it begins fusing heavier and heavier elements. Helium becomes carbon, carbon becomes oxygen, and the process continues. Each step produces energy, but less efficiently than the last. And eventually, the star reaches a point where it tries to fuse iron. That's where things stop working. Iron doesn't release energy when fused. Instead, it consumes it. So, rather than supporting the star against gravity, the core suddenly loses its ability to push outward. And when that happens, gravity takes over. The core begins to collapse. Not slowly, not gently, but rapidly. In a fraction of a second, the inner regions of the star fall inward, compressing more and more as they go. The density increases dramatically. The pressure rises beyond anything we can easily imagine. And then, something remarkable happens. The outer layers of the star, still moving inward, suddenly encounter the incredibly dense core. They rebound, creating a powerful shockwave that moves outward through the star. This is what we see as a supernova, a brilliant, explosive event that can outshine entire galaxies for a short time. From a distance, it looks like a sudden burst of light. A star that was once steady becomes extraordinarily bright, then fades away over weeks or months. But behind that flash, something else has formed. The core, what remains after the collapse, has become incredibly dense. Now, depending on how massive that core is, one of two things happens. If it's below a certain threshold, the collapse stops at what we call a neutron star, a dense object made mostly of neutrons, packed together so tightly that a single teaspoon of its material would weigh billions of tons. But if the core is massive enough, even that isn't enough to stop the collapse. Gravity continues pulling inward. There's no known force strong enough to resist it, and so the core keeps collapsing, shrinking further and further, becoming denser and denser, until it reaches a point where something fundamental changes. The escape velocity exceeds the speed of light. And that's the moment a black hole is born. It's not a loud event, at least not in the way we might imagine. The supernova itself can be spectacular, but the formation of the black hole is more like a quiet disappearance. The core doesn't explode. It doesn't send out a signal saying, "I'm becoming a black hole now." It simply crosses a threshold, and beyond that threshold it becomes something from which nothing can return. What's left behind is not a glowing object, but a region of space defined by its gravity. A place where the inward pull is so strong that all paths lead deeper inside, and from the outside, once the surrounding material settles, it can appear almost still. Just a quiet point in space, invisible. Now, one of the interesting things about this process is how different it is from what we might expect. We often imagine dramatic endings, something chaotic, unpredictable, violent. And while the supernova can be energetic, the final result, the black hole itself, is surprisingly simple. It doesn't retain the complexity of the star that formed it. It doesn't carry visible traces of its past. In many ways, it's stripped down to just a few basic properties: mass, spin, and charge, though in most cases charge is negligible. That's it. All the structure of the original star, all the layers, the elements, the history, all of that is no longer visible from the outside. It's a bit like taking an incredibly detailed object and reducing it to a few simple numbers, and that simplicity is part of what makes black holes so unusual. They're both the result of very complex processes and, at the same time, some of the simplest objects in the universe, in terms of how we can describe them. Now, it's worth noting that not all black holes form in exactly this way. The scenario we just walked through, the collapse of a massive star, is one of the primary ways we get what are called stellar mass black holes. These are black holes with masses ranging from a few times that of the Sun to perhaps a few dozen times, but as we'll see later, there are black holes that are far more massive than this, and their origins are still an active area of research. For now, though, it helps to stay with this idea. A star lives its life in balance. It burns its fuel, maintains its structure, shines steadily. Then, as the fuel runs out, the balance shifts. Gravity, which was always there, quietly waiting, begins to dominate, and in the final moments that inward pull becomes unstoppable. The star collapses, the core crosses a boundary, and a black hole forms. There's something almost natural about it. Not abrupt, not random, but a continuation of the same forces that shape the star from the beginning. Gravity pulling inward, energy pushing outward, and eventually the balance tipping in one direction. If you zoom out, it's part of a larger cycle. Stars form from clouds of gas, live their lives, and then return their material to space, sometimes in dramatic ways, sometimes more quietly. Black holes are just one possible outcome in that cycle, a very extreme outcome, but still part of the same overall pattern. And once they form, they don't just sit completely isolated. They can interact with their surroundings, influence nearby stars, sometimes grow by pulling in additional material. In certain conditions, they can become very active, producing powerful radiation as matter falls inward. Other times, they remain quiet, almost hidden, detectable only through subtle gravitational effects. It all depends on what's around them, which is something we'll begin to explore next. Because while the process we've described gives us a general picture of how black holes are born, the ones that come from collapsing stars are just the beginning. There are many of them, scattered throughout galaxies, each with its own history, its own environment, and among them, there are some that stand out. Not because they break the rules, but because they push them to their limits. A quiet shift in scale can make a surprising difference, especially when we move from dramatic stellar endings to what's left behind afterward. Up to now, we've been talking about how black holes are born, how massive stars collapse, and how something incredibly dense forms at the centre. But not all black holes are enormous, and not all of them dominate their surroundings in obvious ways. Some are much smaller, quieter, and harder to notice. In fact, many of them are so subtle that we only discovered them quite recently, almost by accident. These are often called stellar mass black holes, and among them are some of the smallest known black holes we've ever found. Still massive by everyday standards, of course, but on the lower end of what a black hole can be. And interestingly, these smaller ones can sometimes tell us more about the universe than their larger, more dramatic counterparts. Because they sit right at the edge of what's possible. When a star collapses, the result depends heavily on its mass. If it's too small, it becomes a white dwarf. If it's slightly larger, it may form a neutron star. But there's a narrow boundary between neutron stars and black holes, a kind of dividing line where the outcome isn't always obvious. And for a long time, scientists believed there was a gap, a mass gap. Neutron stars seem to top out at around 2 to 3 times the mass of the Sun. Black holes, on the other hand, were typically observed at 5 solar masses or more. That left an awkward space in between, where we didn't see anything at all. It was as if nature avoided making objects in that range. But as we improved our observations, that assumption began to change. One of the most intriguing discoveries in this area is a black hole known as the unicorn. The name sounds almost whimsical, like something out of a story, but the object itself is quite real. It's located in the constellation Monoceros, which fittingly means unicorn, and for a while it stood out as one of the smallest black holes ever detected. What makes it special is its mass. The unicorn is estimated to be about 3 times the mass of the Sun. That places it right in that previously empty gap between neutron stars and black holes. Too heavy to be a neutron star, but lighter than most known black holes. And what's even more interesting is how we found it. Unlike some black holes that reveal themselves through bright X-ray emissions, the unicorn is relatively quiet. It doesn't have a large accretion disk glowing with intense radiation. It's not actively feeding in a dramatic way. Instead, It was discovered through its effect on a nearby companion star. Astronomers noticed that this star was moving in a way that suggested it was orbiting something unseen. By carefully measuring its motion, they could estimate the mass of the invisible companion, and once again the numbers pointed to something unusual. Too massive to be anything ordinary. Invisible, compact. A black hole, but a smaller one than expected. It's a bit like finding a new type of object that sits right between two categories you thought were separate. It forces you to reconsider the boundaries, to ask whether the division was ever real in the first place. And that's exactly what happened here. The unicorn suggested that black holes could exist at lower masses than we had previously observed, that the gap might not be a true gap at all, but simply a region we hadn't explored carefully enough yet. Now, the unicorn isn't the only example. Another object, with a slightly less poetic name, is XTEJ 1650-500. This one was detected earlier, and it also falls on the lower end of the black hole mass range. It's part of a binary system much like Cygnus X1, where material from a companion star is being pulled toward the black hole, and as that material spirals inward, it heats up, producing X-rays that we can detect from Earth. That's actually what the XTE in its name refers to. The Rossi X-ray Timing Explorer, a space telescope that played a key role in identifying such objects. By studying the X-rays and the motion of the companion star, astronomers were able to estimate the mass of XTEJ 1650-500, and once again, it came out relatively low for a black hole, just a few times the mass of the Sun. Not as small as the unicorn, but still close to that boundary. And then there's GRS 1009-45, sometimes written differently depending on the catalogue, but often grouped with these lower mass candidates. This system also involves a black hole paired with a companion star, and like the others, it reveals itself through the behaviour of that star and the radiation emitted as material falls inward. What's consistent across all these cases is the method of discovery. We're not seeing the black hole directly. We're watching how it influences its surroundings. We're measuring motion, detecting radiation, and using those clues to build a picture of something that remains invisible. And in doing so, we've started to fill in that mass gap. Now this might seem like a small detail, just a few solar masses here or there, but it has important implications. Because it tells us something about how stars collapse. If black holes can form at lower masses than we thought, it suggests that the process of collapse is more flexible than we assumed. That the boundary between neutron stars and black holes isn't a sharp line, but more of a gradual transition. And that raises further questions. What determines exactly where that transition happens? Is it just mass, or are there other factors involved? Rotation, composition, the dynamics of the collapse itself. These are still active areas of research, and each new discovery adds a piece to the puzzle. But there's also something else worth noticing here. These smaller black holes are often quieter. They don't always produce dramatic emissions. They don't always announce their presence with bright signals. In many cases, they're just there, orbiting a companion star, influencing its motion, but otherwise blending into the background. It's a reminder that the universe isn't always loud about its most interesting features. Sometimes the most important discoveries come from subtle effects, small deviations, slight irregularities, things that don't quite fit the expected pattern. And it takes careful observation, patience, and a willingness to question assumptions to notice them. Now, if you step back for a moment, there's an interesting contrast forming. On one end, we have these relatively small black holes, just a few times the mass of the Sun, quietly orbiting within binary systems. On the other end, there are black holes that are millions or billions of times more massive, sitting at the centres of galaxies. Both are black holes, both follow the same basic rules, but the difference in scale is enormous. It's like comparing a small hill to a mountain range. And yet, the smaller ones are often easier to understand. They come from individual stars, from processes we can model and study in detail. We can trace their origins, follow their evolution, and observe their interactions with nearby objects. The larger ones, as we'll see later, are more mysterious. But for now, staying with these smaller black holes helps ground the idea. It shows that black holes aren't all extreme in the same way. Some are just the natural leftovers of stellar life cycles, the remnants of stars that lived, burned their fuel and collapsed. In a sense, they're part of a recycling process. The outer layers of the star are often expelled into space, enriching the surrounding medium with heavier elements. Those elements can go on to form new stars, new planets, even, eventually, the building blocks of life. And at the centre, what remains is this dense, invisible object. A black hole, quietly continuing its existence. So, while the term black hole might bring to mind something dramatic or even threatening, these smaller ones are in many ways quite ordinary on a cosmic scale. They're common, they're predictable, and they follow directly from the life cycles of stars. Of course, that doesn't make them any less fascinating. If anything, it makes them more so, because they show how something so extreme can arise from processes that are, at their core, quite natural. Far beyond the scattered remnants of collapsed stars, there is another kind of black hole that changes the scale of everything we've talked about so far. Not by a small margin, but by factors so large that they're difficult to hold in your mind all at once. These are the giants, black holes that don't come from a single star, but sit at the centres of entire galaxies, holding millions or even billions of times the mass of our Sun. And unlike the smaller ones drifting quietly through space, these are not easy to ignore. Even when they're calm, their presence shapes everything around them. If you imagine a galaxy as a vast, rotating collection of stars, gas and dust, stretching across tens of thousands of light years, then at its heart, in many cases there is a single point where gravity gathers itself into something far more concentrated, not visible, not shining, but unmistakably there. These are called supermassive black holes. And what's interesting is not just how large they are, but how common they seem to be. For a long time, astronomers suspected that galaxies might contain dense objects at their centres. Observations hinted at unusual motion, stars moving faster than expected, light behaving in ways that suggested a strong gravitational influence. But it took careful, patient measurements to confirm what was really going on. Instead of trying to see the black hole directly, scientists watched the stars near the centre. These stars don't move randomly. They follow precise orbits, just like planets around the Sun. And by tracking those orbits over time, you can calculate the mass of whatever they're orbiting. In our own galaxy, this process took decades. Astronomers observed a group of stars near the centre of the Milky Way, carefully measuring their positions and velocities year after year. Some of these stars move incredibly fast, completing full orbits in just a few years. That alone tells you something is different there, because for a star to move that quickly and stay bound in orbit, the object it's orbiting must be extremely massive. And when the calculations were done, the result was clear. At the centre of our galaxy, there is an object with about 4 million times the mass of the Sun, confined to a region smaller than our solar system. There's no known way to pack that much mass into such a small space without forming a black hole, and so we have Sagittarius A star, the supermassive black hole at the centre of the Milky Way. It's a strange thing to think about. Every star you see in the night sky, every point of light, is part of a system that is, in a way, orbiting around this central object. Not directly, not like planets around a star, but as part of the larger structure of the galaxy. And yet, despite its size, Sagittarius A star is relatively quiet. It's not actively pulling in large amounts of material. It's not producing enormous jets of energy. For the most part, it just sits there, influencing the motion of nearby stars, shaping the gravitational structure of the galaxy. A quiet giant. But not all supermassive black holes are so calm. In other galaxies, especially those known as active galaxies, the central black hole can be much more noticeable. When there is a lot of gas and dust available near the centre, the black hole begins to feed. material spirals inward, forming a bright accretion disk. As it heats up, it can outshine the entire galaxy. This is what we call a quasar, a region so bright that it can be seen across billions of light years. Not because the black hole itself is glowing, but because of the intense energy released by matter falling into it. And sometimes the energy doesn't just stay in the disk. It gets redirected into narrow jets that shoot out from the poles of the black hole, travelling vast distances into space. These jets can extend for thousands of light years, carrying energy far beyond the central region. So while some supermassive black holes are quiet, others are among the most energetic objects in the universe. It all depends on their environment. Whether there's material nearby, whether they're actively feeding or simply waiting. Now, this raises an interesting question. How do these giants form? Because the process we described earlier, the collapse of a single star, can explain black holes up to a certain size. But when you're dealing with millions or billions of solar masses, that explanation isn't enough. You can't just collapse a star to get something that massive. Instead, it's likely that supermassive black holes grow over time. They might begin as smaller black holes, formed from early stars, and then gradually accumulate more mass by pulling in gas, dust, and even merging with other black holes. Over millions or billions of years, they grow larger and larger, eventually reaching the enormous sizes we observe. But there's a complication. Some of the supermassive black holes we've observed existed very early in the universe, less than 1 billion years after the Big Bang. That's not a lot of time for something to grow from a small seed into a billion solar mass object. So, there may be other processes involved. Perhaps some black holes form directly from the collapse of large clouds of gas, bypassing the usual star phase. Or maybe conditions in the early universe allowed for faster growth. We're still working on that part. And that uncertainty is part of what makes these objects so interesting. They don't just sit at the centres of galaxies, they also challenge our understanding of how the universe evolved. Now, another thing to consider is how closely these black holes are connected to their galaxies. There seems to be a relationship between the mass of the central black hole and the properties of the galaxy itself. Larger galaxies tend to have larger black holes. The motion of stars in the galaxy's central region often correlates with the black hole's mass. It's as if they grow together. As the galaxy evolves, the black hole evolves with it, and in some cases the black hole can influence the galaxy's development. The energy released by an active black hole can heat surrounding gas, preventing it from forming new stars. It can push material outward, shaping the structure of the galaxy over time. So these giants are not just passive objects sitting at the centre, they're part of the system, interacting with their surroundings, influencing the behaviour of stars and gas on a large scale. And yet, despite all of this, they remain difficult to observe directly. We can see their effects, we can measure their mass, we can detect the radiation from material falling into them, but the black hole itself remains hidden. Somewhere in the direction of the constellation Sagittarius, hidden behind thick clouds of dust and gas, lies a region we can't see with our eyes, no matter how clear the night sky might be. If you were to look up and try to find it, you wouldn't notice anything unusual. Just stars scattered like always, nothing that immediately stands out, and yet right there, at the very centre of our galaxy, there is something quietly holding everything together. Sagittarius, a star. The name sounds a bit technical at first, but it simply refers to a compact radio source detected in that region. The little star symbol at the end, the asterisk, was added because this source was found to be especially compact and interesting compared to others nearby. But behind that name is something much more significant: a supermassive black hole. Now, we mentioned earlier that many galaxies seem to have these massive objects at their centres, but Sagittarius A star is different in one important way. It's ours. It's the one at the heart of the Milky Way, the galaxy we live in. Which means, in a sense, everything around us is part of a system that includes it. Not in a direct, immediate way, of course. We're far out in one of the spiral arms, tens of thousands of light years away. The Sun orbits the centre of the galaxy once every couple 100 million years, moving along with billions of other stars. But at the centre of that motion, there it is, quiet, unseen, and yet undeniably present. What's interesting about Sagittarius A star is how we came to understand what it is. Because like other black holes, we didn't start by seeing it directly. Instead, we observed what was happening around it. For decades, astronomers focused their attention on the central region of the Milky Way, using telescopes that could see in infrared and radio wavelengths. Visible light doesn't work well there because of the dense clouds of dust blocking the view, but longer wavelengths can pass through, revealing what's hidden behind. And what they found was a cluster of stars moving in very unusual ways. These stars, often called ESA stars, orbit extremely close to the galactic centre, much closer than any stars orbit around our Sun, and they move very fast. One of the most well-studied stars in this group, known as S2, completes an entire orbit in about 16 years. That's remarkably short on a galactic scale. To put it in perspective, Pluto takes about 248 years to orbit the Sun, and that's within our own solar system. For a star to orbit that quickly at such a distance, the object it's orbiting must be incredibly massive. So astronomers tracked these stars over time, carefully mapping their orbits. Each pass, each position, each change in velocity was recorded and analysed, and from that data they could calculate the mass of the central object. The result was about 4 million times the mass of the Sun, but here's the key detail. All of that mass had to be contained within a region smaller than the orbit of Mercury. There's no known way to pack that much mass into such a small space without forming a black hole. And so, Sagittarius A star became one of the strongest pieces of evidence we have for the existence of supermassive black holes. Not because we saw it directly, but because the stars around it left no other explanation. It's a bit like watching leaves swirl around in the wind. You don't see the wind itself, but you know it's there because of how everything moves. Now, what makes Sagittarius a star particularly interesting is how calm it is compared to other supermassive black holes. In many galaxies, the central black hole is actively feeding, pulling in gas and dust, producing enormous amounts of radiation. These are the quasars and active galactic nuclei we talked about earlier, some of the brightest objects in the universe. But Sagittarius A star is quiet. It's not pulling in large amounts of material. There's no bright accretion disk glowing intensely, no massive jets shooting out into space. It's more like a resting giant. Occasionally it does flare up a little. There are brief bursts of activity, small increases in brightness, usually in X-rays or infrared. These are thought to be caused by small amounts of material falling in, perhaps from nearby gas clouds or the outer edges of stars. But these events are relatively minor. Most of the time, Sagittarius A star just sits there doing very little that we can detect. And that's actually quite helpful for us, because a quieter environment makes it easier to observe the stars around it. If there were a lot of radiation and energetic activity, it would be harder to track those precise orbits. The calmness gives us a clearer view of the gravitational effects. So in a way, the fact that it's quiet is part of what allowed us to understand it so well. Now, even though we can't see the black hole itself, we can begin to form a picture of what the region around it looks like. Imagine a dense cluster of stars moving in different directions, some on tight, fast orbits, others farther out. The gravitational pull at the centre dominates everything nearby. If you were somehow able to get close enough, though still at a safe distance, you wouldn't see a glowing object or a visible surface. You'd see stars moving in curved paths, perhaps gas drifting inward, and at the centre, a kind of darkness. Not empty space, but a region where light doesn't escape. In recent years, we've even managed to create an image of Sagittarius, a star's shadow, using a network of telescopes spread across the Earth, working together as a single, planet-sized instrument. The result is not a photograph in the usual sense, but a reconstruction based on radio signals. It shows a bright ring of emission surrounding a darker central region. That dark region is the shadow of the black hole. Not the black hole itself, but the silhouette created by its gravitational effect on light. It's a remarkable achievement because it takes something we've only ever inferred and gives it a kind of visual presence. And yet, even with that image, the black hole remains, in a sense, hidden. We see its outline, its influence, but not the thing itself. There's something fitting about that, because Sagittarius A star has been there for a very long time, quietly shaping the centre of the galaxy, long before we had the tools to detect it, long before we understood what it was. And even now, with all our technology, it still keeps a certain distance. We know it's there. We know how massive it is. We can trace the paths of stars around it. But the interior, what lies beyond the event horizon, remains out of reach, and likely always will. Now, it's worth reflecting for a moment on the scale of this. 4 million suns, compressed into a region smaller than our solar system. It sounds enormous, and it is, but compared to some of the black holes we'll encounter later, Sagittarius A star is actually on the smaller side for a supermassive black hole. There are others out there that are hundreds or even thousands of times more massive, which makes our galaxy's centre feel in a way quite moderate, not too extreme, not too active, just balanced. And perhaps that's part of why the Milky Way looks the way it does. A relatively calm galaxy, with steady star formation, a stable structure, and a central black hole that isn't constantly disrupting its surroundings. Everything in its place, everything moving along its path, and at the centre, this quiet anchor, shaping the motion of stars without drawing attention to itself. What changed everything didn't happen in a single moment of someone pointing a telescope at the sky and suddenly spotting a black hole. It came slowly, through years of preparation, coordination, and a kind of quiet determination shared by scientists across the world. Because if you want to see something as small and distant as a black hole's shadow, you run into a problem almost immediately. They're far away, extremely far away, and even the largest telescopes we have by themselves aren't powerful enough to resolve something that small at that distance. So instead of building one impossibly large telescope, scientists came up with a different idea. They would connect many telescopes together, spread them across the Earth, and use them as if they were one single instrument. This is the Event Horizon Telescope, often shortened to EHT. It's not a telescope in one location, but a network. Observatories in different parts of the world, from deserts to mountaintops, all working together, synchronized with incredible precision. Each one collects data at the same time, and later, all that data is combined. The result is something equivalent to a telescope the size of the Earth, and with that level of resolution, something new became possible. Not seeing a black hole directly, but seeing the region right at the edge of it. The boundary where light bends so strongly that it forms a kind of outline, a shadow. Now, if you're going to attempt something like this for the first time, you don't start with something subtle or quiet. You choose a target that gives you the best possible chance. And that's where M87 comes in. M87 is a galaxy located about 55 million light-years away from us. Which sounds incredibly distant, and it is, but in cosmic terms it's relatively nearby. At its centre is a supermassive black hole that is far larger than Sagittarius A star. We're talking about a mass of around 6.5 billion suns. So even though it's much farther away than the centre of our own galaxy, its sheer size makes it appear larger in the sky, at least from a measurement perspective. That combination, large and relatively close, made it the ideal candidate. And there was another advantage. Unlike Sagittarius A star, which is fairly quiet, the black hole in M87 is active. It has a bright accretion disk, and it produces a massive jet of energy that extends thousands of light years into space. That activity means there's plenty of glowing material around it, which helps outline the region we're trying to observe. So, with the network of telescopes ready and the target selected, the observations began. It wasn't simple. Weather conditions had to be just right across multiple continents. The telescopes needed to be perfectly synchronized, using atomic clocks to ensure that the data lined up accurately. Massive amounts of information were recorded, far too much to send over the internet, so it had to be physically transported on hard drives. Then came the processing. Months of careful analysis, combining signals, filtering noise, reconstructing an image from what is essentially incomplete data. Because even with a global network, you're not capturing every detail directly. You're sampling pieces of information and using them to build a picture. And finally, in 2019, the result was revealed. A ring of light. Soft, slightly uneven, glowing in shades of orange and yellow, and at the centre, a dark region. That dark region is what we call the shadow of the black hole. Not the black hole itself, because by definition that part doesn't emit light, but the effect it has on the surrounding light. Photons travelling near the event horizon are bent, curved, and in some cases trapped entirely. The result is a kind of silhouette, a circular dark area framed by the glowing material around it. It's a simple image, in a way. Not sharp in the way we might expect from modern photography. Not detailed in the sense of showing structures or textures, but incredibly significant. Because for the first time, we had direct visual evidence of something that had only ever been inferred before. A black hole, or at least its immediate boundary, made visible. There's something quietly powerful about that. For decades, black holes were understood through equations, through indirect observations, through the motion of stars and the emission of radiation. All of that evidence was strong, convincing, and widely accepted. But this was different. This was something you could look at. A picture. A reminder that these objects are not just theoretical constructs, but real features of the universe. Now, it's worth taking a closer look at what we're actually seeing in that image. The bright ring is formed by hot gas in the accretion disk, moving at incredibly high speeds as it spirals inward. Because of the extreme gravity, light from this material is bent around the black hole, creating a distorted, circular appearance. Interestingly, one side of the ring appears brighter than the other. That's due to the motion of the gas. The material moving toward us appears brighter because of a relativistic effect called Doppler boosting, while the material moving away appears dimmer. So even in this simple image, you're seeing the effects of motion, gravity, and relativity all at once. And the dark centre, the shadow, is slightly larger than the actual event horizon. This is because of the way light is bent around the black hole. The shadow represents the region from which light cannot reach us, either because it falls in or is redirected away. So what you're seeing is not a direct outline of the event horizon, but a kind of magnified silhouette created by the bending of light. Now, what makes M87's black hole particularly interesting, beyond just being the first one imaged, is how extreme it is. 6.5 billion solar masses. To put that into perspective, if you replaced our Sun with a black hole of that size, its event horizon would extend far beyond the orbit of Pluto. It's a scale that's difficult to visualize, and yet, despite that size, it behaves according to the same principles as the smaller black holes we've talked about. Gravity shaping space, light bending, time stretching. The same rules, just applied on a much larger stage. And that's part of what makes black holes so fascinating. No matter how big or small they are, the underlying physics remains consistent. But as the scale increases, the effects become more noticeable, more dramatic, more observable. M87 gave us a clear example of that. A black hole large enough, active enough, and well positioned enough for us to finally see its shadow. And once that was done, naturally attention turned to the next target. Because if we could image one black hole, perhaps we could image another. And that brings us back to Sagittarius A star, the one at the centre of our own galaxy. Imaging it turned out to be more challenging, not because it was smaller, but because it changes more quickly. The material around it moves faster, the environment is more dynamic, making it harder to capture a stable image. But eventually that too was achieved. Still, M87 was the first, the one that opened the door, the one that took something invisible and gave it a form we could share, discuss and study in a new way. And as we continue, we'll move even further into the extremes. Because while M87 is massive, there are black holes that go beyond even that. Objects so large that they challenge our understanding of how such things can exist at all. Trying to picture something that large doesn't really begin with numbers, because numbers, at a certain point, stop being helpful. You can say millions, billions, even trillions, but after a while they all blur together into something abstract. So instead of starting with a number, it might be easier to approach this one more slowly. Imagine taking everything we've talked about so far, the quiet stellar remnants, just a few times the mass of the Sun, the central black hole of our galaxy, 4 million suns gathered into one place, the one in M87, billions of suns, large enough to stretch far beyond our solar system. Now, take a step beyond even that, and then keep going. Because TON 618 sits in a category that feels almost excessive, even by cosmic standards. It's not just large, it's one of the most massive black holes we've ever found, with an estimated mass of around 66 billion suns. 66 billion! It's the kind of number that sounds like it might be a mistake at first, something you'd want to double check just to be sure a decimal point hasn't slipped somewhere along the way. But no, the measurements, as far as we can tell, hold up. TON 618 is real. And it's enormous. Now, rather than focusing only on the number, it helps to think about what that mass actually means in terms of size. A black hole's size is often described by its event horizon, the boundary beyond which nothing can escape. For TON 618, that boundary is so large that if you placed it where our Sun is, it would extend far beyond the orbit of Neptune, reaching deep into what we consider the outer solar system. Not a compact object hidden somewhere in the dark, but something that would fill a vast region of space. And yet, despite that size, it's incredibly far away. TON 618 lies billions of light years from us, in a region of the universe we can only observe as it was long ago. The light we see from it began its journey when the universe was much younger than it is today. Which adds another layer to the story, because not only is this black hole extremely large, it also existed at a time when the universe was still developing. That raises a question that scientists are still trying to answer. How does something get that big, that early? We know that black holes can grow over time. They can pull in matter, merge with other black holes, gradually increasing their mass. But even with those processes, reaching tens of billions of solar masses is not easy. It requires a lot of material, a lot of time, and the right conditions. And yet, here it is. TON 618 is what we call a quasar, which means it's not just a black hole sitting quietly in space, it's actively feeding. There's a massive accretion disk surrounding it, made up of gas and dust spiralling inward. As this material falls closer to the black hole, it heats up, emitting enormous amounts of energy. So much energy, in fact, that the region around TON 618 shines brighter than entire galaxies. That's something worth pausing on. A single object, or more precisely the region immediately around it, outshining hundreds of billions of stars combined. It's not because the black hole itself is glowing, but because of the extreme environment created by matter falling into it. The accretion disk becomes incredibly hot, and as it radiates energy, it turns the black hole into one of the brightest objects in the observable universe. From a distance, what we see is not darkness, but intense light, and at the center of that light, hidden from view, is the black hole itself. Now, if you were to imagine being somewhere near TON 618, at a safe distance of course, the scene would be quite different from the quiet stillness of Sagittarius A star. There would be a bright swirling disk of material, glowing across multiple wavelengths. The motion of gas would be rapid, turbulent and energetic. radiation would stream outward, making the environment far from calm. It's a much more active system, and yet, at its core, the same principles apply. Gravity pulling inward, matter spiraling down, space and time bending under the influence of immense mass. The difference is scale. Everything is amplified, everything is pushed to an extreme, and that's really what makes TON 618 so fascinating. It's not just a larger version of something we already understand, it's a case that stretches our understanding, forcing us to ask whether the processes we know are enough to explain what we're seeing. Because to build a black hole of that size, you need either a very large starting point or an incredibly efficient growth process. Some theories suggest that in the early universe, conditions may have allowed for the direct collapse of massive gas clouds, forming large black holes without going through the usual star phase. Others suggest that rapid accretion, combined with frequent mergers, could allow black holes to grow faster than we initially thought. It's likely that the answer involves a combination of factors, but even so, objects like TON 618 remain at the edge of what we can comfortably explain. Now, there's another aspect to consider. Despite its size and brightness, TON 618 is not unique. It's one of the most extreme examples we know, but there are other quasars, other massive black holes, each with their own characteristics, their own environments, their own histories. The universe, it seems, has no shortage of ways to produce extremes, and yet each one adds a piece to the puzzle. Each observation helps refine our models, adjust our expectations, and expand our understanding of what's possible. It's a gradual process, not unlike how we first came to understand black holes in general, from theory to observation, from observation to deeper questions, and from those questions to new ideas. Now, even though TON 618 represents one of the largest black holes we've found, it's not the end of the story, because size is just one way to define extreme. There are other black holes that stand out not because of how massive they are, but because of how they behave. Some feed at extraordinary rates, some produce jets that extend across vast distances, some appear to grow faster than we can easily explain, and some exist in environments that challenge our assumptions about how black holes interact with their surroundings. Not every black hole is content to sit quietly and wait. Some of them, given the right conditions, become busy. Not in a chaotic or frantic way, but in a steady, continuous process of gathering material, drawing in gas, dust, and sometimes entire stars. And when that happens on a large scale, the result is something that can outshine almost everything else in the universe. These are the black holes that, in a sense, eat too much. Of course, that's a bit of a playful way to describe it, because a black hole doesn't have an appetite or intention. It doesn't decide to consume more. It simply responds to what's around it. If there is material nearby, and if that material drifts close enough, gravity does the rest. But in certain regions of space, especially at the centres of galaxies, there can be an abundance of matter. Clouds of gas, streams of dust, stars orbiting in dense clusters. And under those conditions, a black hole can enter a phase where it's actively pulling in large amounts of material. Now, what's interesting is that the black hole itself doesn't shine as it does this. The brightness comes from everything just outside it. As matter falls toward the black hole, it doesn't simply drop straight in. Instead, it forms a disk, flattening out as it orbits, gradually spiraling inward. This is the accretion disk we've mentioned before, but here it becomes something much more intense. The material in the disk moves incredibly fast, sometimes approaching a significant fraction of the speed of light, and as it moves it rubs against other material, creating friction. That friction generates heat, a lot of heat. Temperatures in these disks can reach millions of degrees, hot enough to emit light across the entire electromagnetic spectrum, from visible light to X-rays and beyond. So even though the black hole itself remains dark, the region around it becomes extraordinarily bright. Bright enough, in some cases, to outshine the entire galaxy that surrounds it. That's what we call a quasar. The term itself comes from quasi-stellar object, because when they were first discovered, they looked like stars, small points of light, but with unusual properties. Over time, it became clear that these were not stars at all, but incredibly distant and powerful sources of energy. At the centre of each quasar is a supermassive black hole actively feeding, and the more material it has access to, the brighter it becomes. Now, there is a limit to how fast a black hole can eat. This is known as the Eddington limit, and it describes a balance between the inward pull of gravity and the outward push of radiation. As material falls in and heats up, it emits radiation, and that radiation pushes outward on the surrounding gas. If the black hole tries to pull in material too quickly, the radiation pressure increases, pushing some of that material away. So in a way, there's a natural speed limit. But even at that limit, the amount of energy involved is enormous, and some black holes appear to operate very close to it, continuously pulling in matter and converting a portion of that mass into energy. This process is actually one of the most efficient ways of generating energy in the universe. More efficient than nuclear fusion, more efficient than almost anything else we know, which is why quasars can be so incredibly bright. Now, from a distance, a quasar doesn't look like a black hole at all. It appears as a brilliant point of light, often brighter than the combined light of billions of stars. And because they're so luminous, we can see them across vast distances, looking back billions of years into the early universe. In fact, many of the quasars we observe are among the most distant objects we can detect. They give us a glimpse into a time when galaxies were still forming, when black holes were growing rapidly, when the universe itself was much younger. And that's another interesting aspect of these overactive black holes. They seem to have been more common in the early universe. Back then there was more gas available, more material to feed on, and conditions that allowed black holes to grow quickly. Over time, as galaxies evolved and the available material was used up or dispersed, many of these black holes settled into quieter states. So when we observe a quasar today, we're often looking at a phase that happened long ago, a period of intense growth and activity. Now, not all feeding black holes are as extreme as quasars. There are also less active ones, sometimes called active galactic nuclei, or AGN for short. These still involve accretion disks and energy release, but at a lower level. They might produce steady radiation, occasional flares or moderate jets depending on the environment, and that environment plays a crucial role, because a black hole can only eat what's available. If there's little material nearby, it remains quiet. If there's a lot, it becomes active. It's not a change in the black hole itself, but in its surroundings. Now, sometimes the feeding process can become quite dramatic. A star might wander too close, crossing what's known as the tidal disruption radius. At that point, the gravitational difference between one side of the star and the other becomes so strong that the star is pulled apart. Not instantly, but stretched and torn, its material forming a stream that spirals toward the black hole. This is called a tidal disruption event, and for a brief period, it can cause a sudden increase in brightness, a flare that signals something has been consumed. Again, not in a sudden gulp, but in a gradual process. Material falling in, heating up, emitting energy, and eventually disappearing beyond the event horizon. There's something almost methodical about it. Even in these more extreme cases, the process follows the same underlying rules: gravity, motion, energy conversion, all playing out on a larger and more intense scale. Now, one of the most striking features of some actively feeding black holes is the presence of jets. These are narrow beams of particles and energy that are launched from the regions near the black hole, extending far into space. The exact mechanism behind these jets is still an area of active research, but it likely involves magnetic fields interacting with the rotating accretion disk and the black hole itself. The result is a focused stream of energy that can travel thousands, sometimes even millions, of light years, and these jets can have significant effects on their surroundings. They can heat up gas in the galaxy, prevent new stars from forming, or shape the structure of the intergalactic medium. So in a sense, a feeding black hole doesn't just consume, it also influences, It redistributes energy. It affects its environment on a large scale, and that's an important point. Because when we talk about black holes eating too much, it's not just about how much material they take in. It's about how that process changes everything around them. From the immediate accretion disk to the larger galaxy, the effects can be far-reaching. And yet, despite all this activity, the black hole itself remains hidden. At the center of all that light, all that motion, all that energy, there is still a region we cannot see into, a boundary beyond which information doesn't return. Which brings us to an interesting transition, because while some black holes grow steadily over time, feeding at rates that we can measure and understand, there are others that seem to grow much faster than expected. Black holes that, especially in the early universe, reached enormous sizes in surprisingly short periods. Out in the deeper reaches of the universe, there are a few black holes that don't just grow, they seem to rush, not in a chaotic or uncontrolled way, but at a pace that feels almost uncomfortable when you compare it to what we expect. Because by the time we first began to understand how black holes gain mass, there was already a general assumption in place. Growth takes time, even with a steady supply of gas, even with mergers, even with ideal conditions, there are limits to how quickly something can become enormous. And yet when we look far enough away, which is really the same as looking far enough back in time, we begin to find objects that don't quite follow that expectation. They're already massive, already active, already shining intensely, at a point in the universe's history when, by our standard models, they probably shouldn't be. One of the most striking examples is something known as J0529-4351. The name, as usual, is a bit of a coordinate label, pointing to its location in the sky, but what matters more is what it represents. This object is one of the most luminous quasars ever observed, powered by a black hole that is not only extremely large, but growing at a rate that pushes the limits of what we thought possible. It's not just feeding, it's feeding efficiently, continuously. Pulling in matter at a rate that suggests a near-perfect balance between gravity drawing material inward and radiation pushing outward, right at that threshold we talked about earlier, the Eddington limit. But what makes J0529-4351 stand out is how steady that process appears to be. It's not flaring unpredictably, it's not showing signs of instability. Instead, it's behaving like a system that has settled into a kind of optimal growth mode, steadily converting mass into energy and doing so on a scale that's difficult to match. And because it's so bright, we can observe it from a very great distance, which means we're seeing it as it was billions of years ago, a time when the universe was still relatively young. Now that's where the puzzle begins, because to reach such a high mass so early, something had to happen differently. Either it started from a much larger initial seed, perhaps forming directly from a massive gas cloud instead of a single star, or it grew at an unusually fast rate for a sustained period. Possibly both. And that brings us to another example, J1144-4308. This one adds a slightly different twist. While it also represents a rapidly growing black hole, what stands out here is the environment it exists in. Observations suggest that the region around it is rich in material, with a steady inflow of gas feeding the central black hole. It's not just that the black hole is capable of fast growth, it's that the conditions around it allow that growth to continue without interruption. Think of it less like a sudden surge, and more like a continuous stream. As long as the supply holds, the process continues. And in the early universe, there was more of that supply available. Galaxies were forming, gas was abundant, and structures were still coming together. It was, in a sense, a more active time. So black holes like J1144-4308 might represent systems that took full advantage of those conditions, growing steadily, efficiently, and without the limitations we see in more mature galaxies. But even with that explanation, there's still something that feels slightly out of place, because even under ideal conditions there are limits, and yet some of these objects seem to be right at those limits, or possibly even pushing beyond them in ways we're still trying to understand. Now, RACSJ 0320-35 adds another layer to this picture. This one is interesting not just because of its growth rate, but because of how it was discovered and what it tells us about the population of black holes we might be missing. Detected through radio observations, RACSJ 0320-35 highlights the importance of looking at the universe in different wavelengths. Not all black holes reveal themselves in the same way. Some are bright invisible light, others in X-rays, and some primarily in radio frequencies. And when you start combining all these different observations, you begin to see a broader picture. There are more active, rapidly growing black holes out there than we initially realized. Some are hidden behind dust, some are oriented in ways that make them harder to detect, and some are simply too distant or too faint in certain wavelengths to stand out until we look in the right way. RACSJ 0320-35 suggests that what we're seeing might only be part of the story. There could be many more of these fast-growing systems quietly building mass in the early universe, contributing to the population of supermassive black holes we see today. Now, when we talk about fast growth in this context, it's important to keep the scale in mind. We're not talking about something that changes dramatically over days or even years. This is still a process that unfolds over millions of years, but compared to the typical timescales we expect for black hole growth, it's accelerated, efficient, relentless in a way, but not chaotic. And that's a key distinction. Even these extreme systems follow the same basic principles. Material falls in, energy is released, gravity and radiation balance each other. It's just that everything is happening at the upper limits of those processes, which brings us back to the central question. How do you get something so massive so early? There are a few leading ideas. One is the concept of direct collapse. Instead of forming from a star, a massive cloud of gas collapses directly into a black hole, skipping the intermediate steps. This would create a much larger initial seed, giving the black hole a head start. Another possibility is sustained super-Eddington accretion, where the black hole temporarily exceeds the usual growth limits, perhaps due to specific conditions in the surrounding gas that reduce the effect of radiation pressure. And then there's the role of mergers. In the early universe, galaxies were closer together, interactions were more common, and black holes could merge more frequently, combining their masses and accelerating growth. It's likely that the reality involves some combination of all these processes, different black holes, in different environments, following slightly different paths, but all contributing to the same outcome, a population of massive objects that appear earlier and grow faster than we once thought possible. And what's particularly interesting is how these early giants connect to what we see today. The supermassive black holes at the centres of galaxies didn't just appear fully formed, they grew over time through processes like these. So when we observe something like J0529-4351 or J1144-4308, we're not just looking at an isolated case, we're looking at a stage in a much larger story, a glimpse of how the universe built its most massive structures. If you keep looking farther and farther into space, something interesting begins to happen. Not visually at first, because distant galaxies still appear as faint points of light, sometimes blurred, sometimes stretched by gravity. But conceptually, something shifts. The farther away an object is, the longer its light has been travelling to reach us. Which means you're not just looking across distance anymore, you're looking back in time. 1 billion light years away means you're seeing something as it was 1 billion years ago. 10 billion light years away, and you're seeing it when the universe was still very young. So when we talk about the oldest black holes we can see, we're not talking about objects that are physically old in the sense of aging slowly over time. We're talking about black holes whose light has taken so long to reach us that we observe them as they existed near the beginning of the universe, and that's where things start to feel a little unusual. Because when astronomers began searching the distant universe, they expected to find early galaxies, early stars, structures that were still forming, still organising themselves into the patterns we see today. And they did find those things. But they also found something else, very bright, very distant quasars, which as we've seen means very large black holes. And not just moderately large, but already massive, hundreds of millions, sometimes billions of times the mass of the Sun, appearing at a time when the universe was less than 1 billion years old. Now that's not impossible, but it is unexpected, because it suggests that black holes didn't just appear later, after galaxies had time to evolve and mature. They were already there, already significant, already influencing their surroundings very early on. It's a bit like walking into a forest that you expect to be newly planted, only to find towering trees already in place. You begin to wonder how they got there so quickly. One of the most distant and oldest known black holes is found in a quasar called ULA-SJ 112 0+0641. Again, the name itself isn't particularly memorable, but what it represents is quite remarkable. The light from this object has travelled for more than 13 billion years to reach us. That means we're seeing it as it was when the universe was only about 770 million years old. And at that time, at its centre, there was already a black hole with a mass of about 2 billion suns. 2 billion. In less than 1 billion years of cosmic history. That's the part that continues to draw attention. Because even with steady growth, even with favourable conditions, reaching that size so early requires something beyond the simplest models. Now, one way to think about this is to consider the environment of the early universe. It was denser, there was more gas available, galaxies were closer together, interactions were more frequent, and the overall conditions were more dynamic. In such an environment, it might be easier for black holes to grow quickly. But even so, there are limits. And that's why these early black holes are so important. They serve as constraints, as benchmarks, that any theory of black hole formation and growth must be able to explain. If your model can't produce a billion solar mass black hole within the first billion years, then something is missing. And that's where current research is focused. Trying to understand whether the initial seeds were larger than we thought, whether growth rates could have been higher, or whether there are additional processes we haven't fully accounted for yet. Now, beyond their size, these early black holes also tell us something about the state of the universe at the time. Remember the epoch of reionization we mentioned earlier? This was a period when the first sources of light began to ionize the neutral hydrogen that filled the universe after the Big Bang. Before this period, the universe was largely opaque to certain wavelengths of light. After it became more transparent. Quasars, including those powered by early black holes, likely contributed to this process. Their intense radiation would have affected the surrounding gas, changing its properties, influencing how light travelled through space. So when we observe these distant quasars, we're not just seeing black holes, we're seeing markers of a transition. A time when the universe was changing from a relatively simple state to something more structured and complex. And that makes them valuable in more ways than one. They help us understand black holes, but they also help us understand the broader evolution of the universe. Now, there's another subtle point here. When we say these are the oldest black holes we can see, we're really talking about the earliest ones that are visible to us. There may be older ones, or earlier ones, that we simply can't detect yet. Perhaps they're too faint, perhaps they don't produce enough radiation, or perhaps they exist in regions we haven't observed in enough detail. So our picture is still incomplete. We're seeing the brightest examples, the most active ones, the ones that stand out against the background. But there may be many more, quieter black holes from the same era, hidden from our current instruments. And as technology improves, as telescopes become more sensitive, we may begin to uncover more of these early objects, filling in the gaps, extending the timeline, getting a clearer sense of how black holes emerged and evolved alongside galaxies. Now, it's also worth noting that these early black holes don't necessarily look very different from later ones in terms of their basic behaviour. They still have accretion disks, they still emit radiation, they still follow the same physical principles. What's different is the context, the environment they exist in, the time period they belong to, and the fact that they reach such significant sizes so quickly. That combination makes them stand out. Instead of thinking about black holes as dark and hidden, It helps to shift perspective for a moment and consider how some of them become the brightest things we can observe in the entire universe. That sounds a bit contradictory at first. A black hole, something defined by the fact that light cannot escape it, somehow becoming a source of extraordinary brightness. But as we've already begun to see, the light doesn't come from the black hole itself. It comes from everything happening just outside it, and in some cases that just outside becomes incredibly energetic. When a supermassive black hole is actively feeding, surrounded by large amounts of gas and dust, the accretion disk forms and begins to glow. That's already impressive, reaching temperatures and brightness levels that can outshine entire galaxies. But sometimes, the process goes a step further. Under the right conditions, a portion of the energy doesn't stay confined to the disk. Instead, it gets channeled into narrow, focused streams that shoot outward from the regions near the black hole. These are known as jets. They're not random or scattered. They're highly organized, extending in opposite directions from the poles of the black hole, perpendicular to the accretion disk, and they can travel vast distances, sometimes stretching for thousands or even millions of light years. Now, if one of these jets happens to be pointed in our direction, the effect becomes even more pronounced. Because of the way the particles in the jet are moving, often at speeds very close to the speed of light, the radiation they emit becomes concentrated along the direction of motion. This is a relativistic effect, where the light is essentially boosted toward the observer. The result is something we call a blazar, and blazars are among the brightest objects in the observable universe. From our perspective, they can appear as intense, flickering points of light, changing in brightness over relatively short periods of time, not because the black hole itself is fluctuating wildly, but because the processes in the jet, the movement of particles, the structure of the magnetic fields can vary. So what we're seeing is not just a steady glow, but a dynamic system, a beam of energy directed across space. Now, one of the most well-known examples of this is a blazar called 3C279. It lies billions of light years away, yet it's still detectable because of the enormous amount of energy being directed toward us. Observations of objects like this help scientists understand how jets form, how energy is transported, and how black holes interact with their surroundings. But beyond individual examples, what's really interesting is the scale of influence these jets can have. They don't just exist near the black hole, they extend far beyond it, interacting with the interstellar medium, heating gas, affecting star formation, and in some cases shaping the structure of the galaxy itself. So in a sense, these black holes are not just consuming material, they're also redistributing energy. They're affecting regions far from their immediate surroundings, and they're doing so in a very focused, directional way. It's quite different from the more symmetrical glow of an accretion disk. Now, if you imagine being somewhere in a galaxy with an active jet, but not directly in its path, the black hole might still appear as a bright central region, surrounded by glowing material. The jet would extend outward, perhaps visible as a narrow beam stretching into space. But if you were aligned with that jet looking straight into it, the brightness would be much more intense. That's essentially what happens with blazars. We're looking almost directly down the path of the jet, and that alignment makes all the difference. Now, it's worth noting that not all active black holes produce strong jets. The exact conditions required for jet formation are still being studied, but they likely involve the spin of the black hole, the structure of the magnetic fields, and the properties of the accretion disk. Some black holes spin very rapidly, dragging space around them in a process known as frame dragging. This rotation can help organize magnetic fields in a way that channels energy outward along the poles. Others, with different conditions, may not produce such pronounced jets. So again, there's variety. Even among these extreme cases, not all black holes behave the same way. But when they do produce jets, the result can be striking, and it changes how we think about black holes. Because instead of being purely absorptive, simply pulling things inward, they become part of a larger energy cycle. Material falls in, energy is released. Some of that energy is directed outward, sometimes across vast distances, and that outward flow can influence the formation of stars, the distribution of gas, and the evolution of galaxies. Now, there's something almost balanced about that. Even in these extreme environments, there's a kind of exchange. Not a perfect symmetry, but a process where inward and outward flows are connected. And that connection becomes especially visible in these bright beacons. Objects that, despite being powered by something fundamentally dark, become some of the most luminous features in the cosmos. It's a bit like seeing the effect of something without seeing the thing itself. The black hole remains hidden, but its presence is unmistakable. Now, as we continue, it's helpful to keep in mind that brightness is just one way to define extreme. We've looked at size, growth, age, and now energy output, but there are also black holes that stand out because they behave in ways we didn't initially expect. Every so often, just when things begin to feel understandable, the universe introduces something that doesn't quite fit the pattern. Not completely wrong, not breaking the rules outright, but just different enough to make you pause and look again. Black holes, for all their consistency and how they're defined, are no exception to this. Once scientists became comfortable with the idea of stellar mass black holes and supermassive ones at galactic centers, a kind of expectation formed. A quiet assumption about where black holes should be, how they should behave, and what environments they should belong to. And then, naturally, a few of them refuse to follow that script. Some black holes are not sitting neatly at the center of a galaxy. Some are not part of stable systems. Some appear to be moving, displaced, or existing in ways that raise more questions than answers. These are the strange ones. Now, one of the first surprises came from observations of galaxies where the central black hole didn't seem to be central. Astronomers expect that over time, a supermassive black hole settles into the exact center of its galaxy. Gravity pulls everything inward, and eventually the most massive object ends up right at the bottom of that gravitational well. But in some cases, the brightest activity, the strongest emissions, appeared to be slightly offset. Not dramatically far away, but noticeably not at the exact center. At first, this might seem like a measurement issue. Maybe the center was misidentified, or the data wasn't precise enough. But as observations improved, it became clear that in certain galaxies the black hole really was displaced. One explanation for this involves galaxy mergers. When two galaxies collide, their central black holes don't immediately merge. Instead, they begin a kind of slow dance, orbiting each other as the surrounding stars and gas settle into a new structure. Eventually, the two black holes spiral inward and combine, releasing energy in the form of gravitational waves. But that merger doesn't always end quietly. If the gravitational waves are emitted asymmetrically, meaning more energy is released in one direction than another, the newly formed black hole can receive a kind of kick. And that kick can send it moving away from the center of the galaxy. Not forever, necessarily, but enough to create a noticeable offset. These are sometimes referred to as recoiling black holes, objects that have been nudged out of their central position by the very process of merging. It's a subtle effect, but one that adds a new layer to our understanding. Black holes are not always perfectly anchored. Under the right conditions, they can move. Now, in more extreme cases, the kick could be strong enough to eject the black hole entirely from its host galaxy. Imagine that for a moment. A supermassive black hole containing millions or billions of solar masses drifting through intergalactic space, no longer bound to a galaxy. It wouldn't be easy to detect, of course, unless it carried some surrounding material with it. But the possibility exists, and that's one of the things that makes these objects so intriguing. They're not just fixed points in space. They can have histories, interactions, even trajectories. Now, there are also smaller scale examples of unusual behavior. Some black holes appear to wander within their galaxies, not because they were kicked out, but because they formed in unusual environments or haven't yet settled into a stable position. Others are found in places where we wouldn't necessarily expect them. For example, There are candidate black holes located in dense star clusters, not at the centre of a galaxy, but within a tightly packed group of stars. These are sometimes referred to as intermediate mass black holes. They're larger than typical stellar mass black holes, but smaller than the supermassive ones, and they're relatively rare, or at least difficult to confirm. Their existence helps fill in a gap between the two main categories, but also raises questions about how they form. Do they grow from smaller black holes through repeated mergers? Do they form directly from massive stars in dense environments? Or is there another pathway we haven't fully identified yet? The answers are still being explored. Then there are black holes that behave in ways that seem almost inconsistent. For instance, some appear to be producing jets in directions that don't align with what we'd expect based on their accretion disks. Others show variability in their emissions that's difficult to explain with simple models. And in a few cases, observations suggest that black holes might be interacting with their surroundings in more complex ways than we initially thought. Not breaking the laws of physics, but revealing that those laws can produce outcomes that are less straightforward than our early assumptions suggested. There's also the case of what are sometimes called wandering black holes. These are objects that move through the galaxy without being tied to a visible system. They might have formed from a star that was part of a binary system, where the companion was lost during a supernova. Or they might have been displaced during gravitational interactions. Either way, they're out there, moving through space, largely undetectable, unless they pass near something that reveals them. It's a bit like having invisible travellers crossing the galaxy. Quiet, unnoticed, but very much present. Now, one of the more unusual discoveries in recent years involves what appears to be a black hole that left a visible trail behind it. In this case, astronomers observed a long, narrow streak of star formation, stretching across space with a candidate black hole at one end. The idea is that as the black hole moved through the gas, it compressed the material, triggering the formation of new stars along its path. So instead of being purely destructive, it may have played a role in creating new structures. Again, it's not entirely outside the laws of physics, but it's not the first scenario that comes to mind when thinking about black holes. And that's really the theme here. Once you start looking more closely, you find that black holes don't always fit into neat categories. They follow the same basic principles, but the outcomes can vary depending on the environment, the history, and the interactions involved. Some stay at the centre, some move, some grow steadily, some merge, some influence their surroundings in subtle ways, others in more dramatic ones. And each of these cases adds another piece to the overall picture, a reminder that even with well-understood rules, the universe can produce a wide range of results. Rather than existing alone, some black holes spend part of their lives in the company of another. Not in a casual sense, but bound together by gravity, orbiting each other in a slow, steady motion that can last for millions or even billions of years. These are binary black hole systems, and in many ways, they're some of the most quietly dynamic structures in the universe. Because even though nothing about a black hole is visible in the usual sense, the motion between two of them creates a kind of pattern, a rhythm, a predictable, gradual change that unfolds over time, and it all begins with proximity. For two black holes to form a pair, they have to come close enough for their gravitational influence to dominate over everything else around them. That can happen in a few different ways. Sometimes it starts with a binary star system. Two massive stars form together, orbiting each other. They live out their lives in parallel, each going through the same stages of fusion, expansion, and eventual collapse. If both stars are massive enough, each one can end its life as a black hole, and if the system remains intact through those transformations, you're left with two black holes orbiting each other. In other cases, the pairing happens later. Two black holes that formed independently might drift close enough in a dense environment, like the centre of a galaxy or a star cluster, to become gravitationally bound. Or as we mentioned earlier, when galaxies merge, their central black holes can eventually find each other and begin orbiting. No matter how the pairing begins, the result is similar. Two objects, each with immense gravity, locked into a mutual orbit. Now, if you were somehow able to observe such a system from a safe distance, it wouldn't look like much at first. No bright glow, no visible surface, just empty space, with perhaps some surrounding material. But if you track the motion carefully, you'd see something remarkable. 2 points, invisible themselves, but influencing the movement of nearby gas or stars, circling around a shared centre. And as time passes, something subtle begins to happen. The orbit starts to shrink, very slowly at first, almost imperceptibly, but steadily. This is because of a phenomenon predicted by Einstein's theory of general relativity. As two massive objects orbit each other, they don't just move through space-time, they disturb it. They create ripples known as gravitational waves that propagate outward at the speed of a light. These waves carry energy away from the system, and as energy is lost, the orbit tightens. The black holes move closer together, faster and faster. Now this process can take an incredibly long time, millions or billions of years of slow spiraling, with the black holes gradually drawing nearer. For most of that time, nothing dramatic happens, just a quiet dance, each orbit slightly smaller than the last. But eventually, as they get close enough, things begin to change more rapidly. The orbital speed increases, the gravitational waves become stronger, and the final stages of the process unfold much more quickly. From the outside, if you had the right instruments, you wouldn't see light, but you would detect something else, a signal, a pattern in space-time itself. And this is where things become especially interesting, because for a long time, gravitational waves were purely theoretical, a prediction from equations, much like black holes themselves once were. But in 2015, that changed. Scientists using the LIGO detectors observed, for the first time, a direct signal of gravitational waves produced by the merger of two black holes. The signal lasted just a fraction of a second, but in that brief moment, it told a story. Two black holes, each about 30 times the mass of the Sun, orbiting each other, spiraling inward, and finally merging into a single, more massive black hole. The energy released in that event, in the form of gravitational waves, was enormous. For a brief instant, the power output exceeded that of all the stars in the observable universe combined. And yet, it wasn't visible light. It was a ripple, a tiny distortion in space-time, detected by measuring changes smaller than the width of a proton. There's something almost delicate about that. Such an immense event producing a signal so subtle that it requires incredibly precise instruments to detect. Now, since that first detection, many more have followed, each one representing a pair of black holes merging somewhere in the universe, each one adding to our understanding of how these systems form and evolve. And from these observations, we've learned a few things. Binary black holes are more common than we once thought. They come in a range of masses, sometimes larger than expected, and their mergers are not rare, but part of an ongoing process happening across the cosmos. Now, if you think about it, this changes the way we view black holes. They're not just isolated endpoints. They're part of a larger cycle. They can form, interact, merge, and grow. Each merger creating a new black hole, often more massive than the ones that came before, and that process can repeat. Over time, building larger and larger structures. Now there's also something interesting about the final moments before a merger. As the black holes get extremely close, their motion becomes incredibly fast. They orbit each other multiple times per second, their paths tightening, their interaction becoming more intense. And then, in a very short period of time, they merge. Not with a collision in the usual sense, but with a smooth transition, forming a single, unified object. The new black hole then settles into a stable state, releasing any remaining energy as gravitational waves, and the process is complete. Two become one, and then once again the system becomes quiet. No visible trace of the event unless there was surrounding material to produce light. Just a new black hole, slightly more massive, slightly different in its properties. It's a subtle transformation, but one that carries a lot of significance, because it shows that black holes are not static. They evolve, they interact, they change over time. There's a moment right at the end of that long, quiet dance when everything changes very quickly. For millions or even billions of years, two black holes can orbit each other in a slow spiral, gradually losing energy, drawing closer bit by bit. If you could watch that process unfold in real time, it would feel almost uneventful for most of its duration. Just two invisible objects tracing loops in space, their motion steady, predictable, calm. And then, near the end, the pace shifts. Not suddenly at first, but noticeably. The orbits tighten, the speed increases. What once took hours or days begins to take seconds, and in those final moments, the entire system compresses into a rapid sequence of motion, each orbit faster than the last, each pass closer than before. This is what's known as the in-spiral phase. It's the point where the two black holes are so close and moving so quickly that the gravitational waves they produce become strong enough to detect from across the universe. If you could translate those waves into sound, which scientists sometimes do for illustration, it would resemble a rising chirp. A low tone that gradually climbs higher and higher as the black holes spiral inward. That sound isn't literal, of course, but it captures the pattern. A build-up, a steady increase, and then a sudden conclusion. Because once the black holes reach a certain point, the separation between them becomes so small that they can no longer maintain separate identities in the same way. They merge, not with a crash or an explosion in the usual sense, but with a smooth, continuous transition. Their event horizons combine, forming a single larger horizon. Their masses unite, along with their spin and other properties. And in that instant, a tremendous amount of energy is released. Not as light, not as heat, but as gravitational waves, ripples in space-time itself spreading outward in all directions at the speed of light. Now, it's worth pausing on that for a moment, because when we say tremendous amount of energy, we're not talking about something modest. In some of these mergers, the energy released in gravitational waves over a fraction of a second can exceed the total energy output of all the stars in the observable universe during that same moment. It's difficult to compare it to anything familiar, and yet, by the time those waves reach us, they are incredibly subtle. By the time they travel across billions of light years, spreading out over space, their effect becomes very small, detectable, but only with instruments of extraordinary sensitivity. This is where observatories like LIGO and Virgo come in. They don't look for light, they measure changes in distance, tiny changes, so small that they are less than a fraction of the width of a proton. The detectors use long perpendicular arms, with laser beams travelling back and forth. When a gravitational wave passes through, it stretches space in one direction and compresses it in another, altering the distance the light travels. And by measuring those changes, scientists can detect the presence of a passing wave. The first time this was done, in 2015, it marked the beginning of a new kind of astronomy. An astronomy not based on light, but on the structure of space-time itself. And the signal that was detected came from exactly this kind of event, two black holes colliding. Now what's interesting is that these events are completely invisible in the traditional sense. If there's no surrounding material, no gas or dust being heated, then the merger produces no light at all. It's silent, dark, and yet it leaves a trace, a ripple that carries information about the masses of the black holes, their spin, their distance, and the nature of their motion. By analysing that ripple, scientists can reconstruct the event. They can determine how large the black holes were, how fast they were moving, and how much energy was released. It's a bit like hearing a sound and being able to tell what caused it, even if you can't see the source. Now, after the merger, the the newly formed black hole doesn't immediately settle into a stable state. For a brief period, it undergoes what's called a ring down. This is similar in a way to how a bell vibrates after being struck. The black hole, now larger and slightly distorted from the merger, emits gravitational waves as it settles into its final, stable shape. These waves have a characteristic pattern, a set of frequencies that depend on the mass and spin of the black hole. And by studying them, scientists can test our understanding of black holes and general relativity. So even after the merger is complete, there's still information being released, a final signature, a kind of settling process. Now, one of the things that makes these collisions so important is that they provide a way to study black holes directly, not through the motion of nearby stars, not through the light from accretion disks, but through the black holes themselves, their masses, their spins, their dynamics. It's a different kind of observation, and it opens up new possibilities, because there are many black hole mergers that occur in environments where no light is produced. Before we had gravitational wave detectors, these events would have gone completely unnoticed. They would have happened quietly, leaving no trace we could detect. But now, we can observe them, we can count them, we can begin to understand how often they occur, how black holes pair up, how they grow over time, and that in turn helps us build a more complete picture of the universe. Now, it's also worth noting that not all black hole collisions are the same. Some involve black holes of similar mass. Others involve one much larger than the other. Some occur in relatively isolated regions, others in dense environments. Each case produces a slightly different gravitational wave signal, a different pattern that reflects the details of the system. And by studying many of these signals, we can start to see patterns, trends, distributions, which tells us something about the population of black holes as a whole. Now, while these events are extremely energetic, they are also, in a sense, very quiet. No explosion in the usual sense, no flash of light, just a ripple passing through space-time, and once that ripple has passed, the system returns to stillness. A new black hole remains, larger than before, perhaps spinning rapidly, but otherwise quiet. It's a transformation that happens in an instant after a long build-up, and then, just as quickly, it's over. Some black holes don't stay where they were born. They don't sit at the centre of a galaxy, anchoring stars in long, predictable orbits. They don't remain part of a stable binary system, circling a companion over millions of years. Instead, they drift, quietly, alone, moving through space with no visible sign of their presence unless something happens to cross their path. These are often called rogue black holes, not because they're behaving unpredictably or breaking any rules, but simply because they're no longer tied to a clear visible system. They've become travellers in a sense, moving through the galaxy without a home. Now, there are a few ways this can happen. One of the most common begins with a binary star system. Two stars orbit each other, much like we discussed earlier. One of them reaches the end of its life first, collapsing into a black hole. If the system remains intact, the second star continues its evolution, eventually reaching the same point. But the process isn't always symmetrical. When a massive star collapses in a supernova, the explosion isn't always perfectly even. If more material is ejected in one direction than another, the remaining core can receive a kind of kick, a push, and if that push is strong enough, it can disrupt the binary system. The black hole might be sent off on its own, no longer bound to its companion. Alternatively, the companion star might be ejected instead, leaving the black hole behind. Either way, the result is a solitary object moving through space. Now, another way a black hole can become a wanderer involves interactions in dense regions of space. In places like star clusters or the centres of galaxies, objects are packed relatively close together. Over time, gravitational interactions can become quite complex. Stars and black holes can pass near each other, exchange energy, and alter each other's trajectories. In some cases, these interactions can fling a black hole out of its original environment. Not at extreme speeds necessarily, but enough to set it on a path that takes it away from the dense region and into the quieter parts of the galaxy. And then there are the more dramatic cases we touched on earlier. When two black holes merge, the emission of gravitational waves can be uneven, producing a recoil, a kick that sends the newly formed black hole moving. In extreme scenarios, that kick could be strong enough to eject it entirely from its host galaxy. Now, detecting these rogue black holes is not straightforward, because as we've seen, a black hole without surrounding material is effectively invisible. No light, no radiation, nothing to observe directly. So how do you find something like that? Once again, the answer lies in observing its effects. One method involves gravitational micro-lensing. If a black hole passes in front of a distant star, its gravity can bend the light from that star, causing it to brighten temporarily. This effect doesn't require the black hole to emit any light of its own. It simply reveals its presence through the way it distorts the light behind it. These events are rare and brief, but they can be detected with careful monitoring of large numbers of stars. And in some cases, the data suggests that the object causing the lensing is a black hole. Another possibility is observing the motion of nearby stars or gas. If something unseen is influencing the movement of visible objects, causing them to accelerate or change direction in ways that don't match the presence of any visible mass, that can point to a hidden black hole. But again, this requires very precise measurements and often long periods of observation. So while we know rogue black holes likely exist in large numbers, we've only identified a small fraction of them so far. Most remain hidden. Now, it's natural to wonder what would happen if one of these wandering black holes passed near our solar system. The idea can sound a bit unsettling at first. An invisible object, several times the mass of the Sun, drifting through space. But in reality, the effects would depend entirely on distance. If a black hole passed far away, say several light years, its influence would be negligible. It wouldn't disrupt the orbits of planets or cause any noticeable changes. If it passed closer, within the outer regions of the solar system, it might begin to perturb the orbits of distant objects, like those in the Oort cloud. But even then, the effects would be gradual, not sudden or catastrophic. Only in the extremely unlikely case of a very close encounter would there be significant disruption. And such encounters are, by all estimates, exceedingly rare. So while the idea of rogue black holes wandering through the galaxy might sound dramatic, their actual impact is usually quite subtle. They move through vast distances of mostly empty space, rarely interacting with anything directly. There's something almost quiet about that. These objects, formed in some of the most energetic events in the universe, end up spending most of their existence drifting through darkness, unseen, unnoticed. Now, there have been a few particularly interesting observations in recent years. In one case, astronomers identified what appears to be a black hole moving through space and leaving behind a trail of star formation. The idea is that as it travels, its gravity compresses gas in its path, triggering the formation of new stars. So instead of simply passing through, it leaves a kind of imprint, a line of newly formed stars marking its trajectory. It's not something we expected to see, but it fits within the broader picture of how gravity influences matter. Even a wandering black hole can shape its surroundings, given the right conditions. Now, stepping back a little, these rogue black holes remind us of something important. That not everything in the universe is neatly organized. Not every object stays where we expect it to. There are processes that can displace, redirect and reshape the distribution of matter over time, and black holes, despite their simplicity in definition, are part of those processes. They can form in one place and end up in another. They can interact, merge, separate. They can be central or they can wander, and each of those possibilities adds to the overall complexity of the universe. Rotation is something we're used to. Planets spin, stars spin, galaxies spin. It's a natural outcome of how matter gathers and moves. When something forms from a cloud of gas, even a slight initial motion can become more pronounced as the material collapses inward. The result is rotation, often smooth, often predictable. But when rotation meets something as dense and extreme as a black hole, the effects become different. Not just faster, but fundamentally more unusual, because a spinning black hole doesn't just rotate in space, it affects the space around it. Now, before we get into that, it helps to start with a simple idea. When an object spins, its outer parts move faster than its inner parts. That's true whether you're looking at a spinning planet or a rotating wheel. The farther you are from the center, the greater the distance you cover in one full rotation, so your speed increases. For black holes, though, this idea takes on a new level of significance, because the boundary we're dealing with, the event horizon, is not a solid surface, but a region defined by gravity. And when the black hole spins, that entire region is affected. A rotating black hole is described by what's known as the Kerr solution, a mathematical model that extends our understanding beyond the simpler, non-rotating case. And one of the key features of a rotating black hole is something called the ergosphere. The name might sound a bit technical, but the concept can be approached gradually. The ergosphere is a region just outside the event horizon where space itself is being dragged around by the rotation of the black hole. Not metaphorically, literally. This effect is known as frame dragging. As the black hole spins, it pulls the fabric of space-time along with it. And within the ergosphere, that dragging becomes so strong that nothing can remain stationary relative to distant observers. Everything is forced to move in the direction of the spin, even light. Now, this doesn't mean that objects are being pulled into the black hole immediately. The ergosphere lies outside the event horizon, so it's still possible, at least in theory, to escape from it. But it's not a place where you can simply hover or remain still. You're carried along by the rotation of space itself. It's a difficult idea to picture, because we don't normally think of space as something that can move, but near a spinning black hole, it does. And the faster the black hole spins, the more pronounced this effect becomes. Now, how fast can a black hole spin? That's an interesting question because there is a limit. In theory, a black hole can spin up to a point where the rotation is extremely close to the speed of light at the event horizon, not exceeding it, but approaching it. This is often described in terms of a dimensionless parameter, where a value of 1 represents the maximum possible spin. In practice, many black holes are thought to spin at values quite close to this limit, which means they are rotating very rapidly. Now, this rotation has several important consequences. First, it changes the shape of the event horizon slightly, making it oblate, flattened at the poles and bulging at the equator. Second, it affects the structure of the accretion disk. Material orbiting a spinning black hole can get closer to the event horizon before becoming unstable compared to a non-rotating black hole. This allows for more efficient energy extraction, meaning that rotating black holes can produce more energetic emissions from their accretion disks. And third, it plays a role in the formation of jets. As we discussed earlier, jets are narrow beams of energy that can extend far into space. The rotation of the black hole, combined with magnetic fields in the accretion disk, can help channel energy into these jets. So in a sense, the spin of a black hole is not just a detail, it's a key factor in how the system behaves. Now, there's also a particularly interesting theoretical idea related to the ergosphere, because within that region, it may be possible, again in theory, to extract energy from the black hole's rotation. This is known as the Penrose process. The idea is that if an object enters the ergosphere and splits into two parts, one part falling into the black hole and the other escaping, the escaping part can carry away more energy than the original object had. That extra energy comes from the rotation of the black hole, so in a way, the black hole can lose rotational energy over time. It's a subtle effect, and not something we can easily observe directly, but it's an example of how these extreme conditions allow for processes that don't occur elsewhere. Now, when we talk about the most extreme spins, we're usually referring to black holes that are rotating very close to their theoretical maximum. Some of these have been inferred from observations of their accretion disks and the radiation they emit. By studying how close the inner edge of the disk is to the event horizon, and how the light is shaped by the black hole's gravity, scientists can estimate the spin, and in some cases the results suggest very high rotation rates. Black holes spinning so fast that the space around them is being dragged along in a significant way. Now, it's worth noting that not all black holes spin rapidly. Some may have relatively low spin, depending on how they formed and how they've evolved. For example, a black hole formed from a single collapsing star might inherit the rotation of that star, while one that has grown through mergers might have a more complex spin history. Each interaction, each merger, each accretion event can alter the spin. So just like mass, spin is something that evolves over time, and that adds another layer of variety to black holes. They're not just defined by how much mass they have, but also by how they rotate. Now, if you take a step back, this idea of spinning black holes adds a new dimension to what we've been discussing. We've looked at size, growth, age, activity, position, and now rotation. Each of these aspects contributes to how a black hole behaves, how it interacts with its surroundings, and how we observe it. And when you combine them, you get a wide range of possibilities. From small, slowly spinning black holes drifting quietly through space, to massive, rapidly rotating ones powering bright quasars and jets, all following the same fundamental rules, but expressing them in different ways. There's a boundary in the universe that doesn't look like a boundary at all. No surface, no line, no visible edge. And yet, once it's crossed, everything changes. This is the event horizon. It's one of the most important features of a black hole, but also one of the most difficult to picture, because it doesn't behave like anything we encounter in everyday life. It's not a wall, not a solid object, not even something you could point to and say, there it is. At least not in the usual sense. Instead, it's a limit. A point in space beyond which escape is no longer possible. Now, that idea can sound a bit abstract at first, so it helps to approach it slowly. Imagine you're far away from a black hole. At that distance, gravity behaves in a familiar way. You could orbit it just as planets orbit stars. You could move closer or farther away, adjust your path, send signals outward, and everything would function as expected. As you move closer, though, something begins to change. The gravitational pull increases, which isn't surprising. But more importantly, the paths available to you, the ways you can move through space, begin to shift. At some distance, you reach a point where escaping becomes more difficult, but still possible if you have enough speed. And then, eventually, you reach the event horizon. At that boundary, the escape velocity equals the speed of light. And since nothing can travel faster than light, there is no longer any path that leads outward. Not because something is actively pulling you in with force, but because the geometry of space itself has changed in such a way that all possible directions now lead inward. That's the key idea. The event horizon is not something that grabs you. It's something that defines what paths are possible. Now, from the perspective of someone falling toward a black hole, the experience might not be as dramatic as you'd expect at that exact moment. If the black hole is large enough, crossing the event horizon wouldn't necessarily involve any sudden physical sensation. No jolt, no impact, no visible marker. You would simply continue moving inward, following the path that gravity has set. But from the perspective of someone watching from far away, things would look very different. As you approach the event horizon, your motion would appear to slow down. More and more. Your signals, the light you emit, would become stretched, shifting toward longer wavelengths, becoming dimmer and dimmer. Eventually you would seem to freeze at the edge, fading from view. To the distant observer, you never quite cross the horizon. You just linger there, becoming less and less visible over time. This difference in perspective is one of the most intriguing aspects of black holes. Time itself behaves differently depending on where you are. Closer to the black hole, time runs more slowly relative to regions farther away, so while you might experience a normal passage of time as you fall in, an external observer sees that process stretched out, almost paused. Now, the event horizon also has an interesting relationship with information. Anything that crosses it is, in a sense, lost to the outside universe. Not just physically, but in terms of what can be known. If an object falls in, we can no longer observe it directly. We can't retrieve information about its internal state. It becomes hidden behind the horizon. And this leads to one of the deeper questions in physics. What happens to that information? Does it disappear entirely? Is it somehow preserved? Or does it exist in a form we don't yet fully understand? This is known as the black hole information paradox, and it's still an open question. Different theories offer different answers, but none have been confirmed definitively. Now, there's another subtle point about the event horizon. It's not something that exists independently of the black hole. It's defined by it. If the mass of the black hole changes, if it grows or shrinks, the event horizon adjusts accordingly. It's a dynamic boundary, not a fixed structure. And in some scenarios, particularly when black holes merge, the shape and size of the event horizon can change in complex ways before settling into a new, stable form. So even this edge is not static. It evolves. Now, from a practical standpoint, the event horizon marks the limit of what we can observe. Everything outside it is in principle accessible. Everything inside it is not. Which means that when we study black holes, we're always looking at the region just outside the horizon. The accretion disk, the motion of nearby stars, the bending of light. All of these give us information about the black hole, but none of them tell us directly what's happening inside. And that's part of what makes black holes so compelling. They represent a boundary not just in space, but in knowledge. A place where our current understanding reaches its limit. Now, it's also worth noting that the concept of an event horizon isn't unique to black holes in a broader sense. There are other situations in physics where horizons appear boundaries beyond which certain information cannot reach an observer. But black holes provide the most extreme example, a clear, well-defined case where the effects are strong enough to be studied in detail. Now, if you imagine being near the event horizon, again, at a safe distance, you would see some unusual effects. Light from behind the black hole would be bent around it, creating distorted images. Stars might appear stretched or duplicated. The sky itself would look different, warped by the curvature of space-time. And as you moved closer, these effects would become more pronounced. But the horizon itself would remain elusive, not a line you can see, but a threshold you can cross. What lies beyond that boundary is something we can't observe, can't measure directly, and can't send any information back from, and yet it's something we keep trying to understand. Because once you accept that black holes exist, once you accept that matter can cross the event horizon and continue inward, the next question feels almost unavoidable. What happens next? Now, it's important to say this carefully. Everything we're about to consider is based on theory, not direct observation, because by definition, whatever happens inside a black hole is hidden from the outside universe. No signal can escape to tell us what's going on. So what we have are models, mathematical descriptions, extrapolations of the laws of physics as we understand them. And those models lead us to an idea known as the singularity. At the very centre of a black hole, according to general relativity, all the mass collapses into a point of infinite density, a place where space is curved to an extreme degree, where time, in a sense, comes to an end. Now, that description sounds very precise, but it comes with a caveat. Infinite in physics often signals that our equations have reached their limit. It doesn't necessarily mean that something truly infinite exists in reality. It may simply mean that the model we're using is no longer sufficient to describe what's happening. So when we talk about a singularity, we're really talking about a place where our current understanding breaks down, a region where general relativity, which works very well on large scales, can no longer fully describe the situation, and where quantum effects, which govern very small scales, likely become important. But we don't yet have a complete theory that combines those two frameworks, so the true nature of what lies at the centre remains uncertain. Now, even though we can't observe the interior, we can still think about how things behave as they approach it. Once an object crosses the event horizon, its future becomes, in a sense, fixed. Not in the everyday meaning of the word, but in a geometric one. All possible paths through space-time lead inward. There's no way to turn around, no direction that leads back out, so the journey continues toward the centre. Now, what that journey feels like depends on the size of the black hole. For a smaller black hole, the difference in gravitational pull between your head and your feet becomes very large very quickly. This leads to what's often called spaghettification, a stretching effect where the object is pulled apart along the direction of the gravitational gradient. It's not a sudden snap, but a gradual elongation. For larger black holes, especially supermassive ones, that effect at the event horizon can be much less noticeable. You might cross the horizon without immediately experiencing extreme stretching. But as you continue inward, the gradients become stronger, and eventually the same process would occur. Now, one of the more unusual aspects of the interior is how space and time behave. Outside a black hole, you can choose your direction of motion. You can move forward, backward, sideways. Inside the event horizon, the structure of space-time changes in such a way that moving toward the centre becomes as inevitable as moving forward in time. In fact, in some descriptions, the roles of space and time effectively switch. The singularity lies in your future, not in a particular direction you can avoid. Just as you can't choose to stop moving forward in time, you can't choose to avoid moving toward the centre once you're inside. It's not a force pushing you. It's the structure of space-time itself guiding your path. Now, this leads to some interesting questions. For example, how long does it take to reach the singularity? From the perspective of the falling object, it's a finite amount of time, not infinite, not endlessly prolonged, a definite duration depending on the size of the black hole. But from the perspective of an external observer, things look very different. As we mentioned earlier, time appears to slow down near the event horizon, so the infalling object seems to take longer and longer to reach it, never quite crossing in the observer's frame. This dual perspective is one of the many ways black holes challenge our intuitive understanding. Now, beyond these classical descriptions, there are many theoretical ideas about what might exist inside a black hole. Some suggest that the singularity is not a point, but a region where quantum effects create a kind of structure, perhaps preventing true infinite density. Others explore the idea that black holes could be connected to other regions of space-time, wormholes, tunnels that link distant points. Though these remain speculative, and there's no evidence that such structures exist in a stable, traversable form. There are also ideas related to quantum gravity, where space and time themselves might have a discrete structure at very small scales. In such theories, the interior of a black hole could behave very differently from what classical models predict. But again, these are areas of ongoing research. We don't yet have a complete picture. Now, there's another aspect to consider. From the outside, we describe black holes using just a few properties: mass, spin, and charge. This is sometimes referred to as the no-hair theorem, the idea that black holes don't retain detailed information about the matter that formed them. But if that's the case, what happens to the information carried by objects that fall in? Does it disappear? Is it somehow encoded on the event horizon? Or does it exist in a form we don't yet understand? This connects back to the information paradox we mentioned earlier, and it remains one of the central questions in modern physics. Now, stepping back a little, it's worth acknowledging that while the interior of a black hole is fascinating, it's also something we may never fully observe. Our understanding will likely come from theory, from indirect evidence, from the way black holes interact with their surroundings, and from the development of new frameworks that unify our current theories. But even without a complete answer, the question itself is valuable, because it pushes us to explore the limits of our knowledge, to refine our models, to consider possibilities that go beyond our everyday experience. Now, as we continue, we'll move from the interior back to a broader perspective, from what might exist inside a black hole to what black holes mean for the universe as a whole. Are they endpoints, final states where matter disappears from the observable universe? Or are they part of a larger process, something that connects to other phenomena, other structures? It's tempting to think of black holes as the final stop, a place where things go and don't come back. Matter falls in, light disappears, and whatever crossed the event horizon is effectively removed from the rest of the universe. From the outside, it looks like an ending. A kind of quiet conclusion to whatever journey brought that material there. But when you look a little closer, that idea becomes less certain. Because in physics, ending is a difficult concept to define. Things tend to transform rather than disappear. Energy changes form. Matter rearranges itself. Processes continue, even when they look still from the outside. And black holes, despite their reputation, may not be quite as final as they first appear. Now, one of the key ideas that challenges the notion of black holes as absolute endpoints comes from quantum mechanics. In the 1970s, Stephen Hawking proposed something unexpected. Black holes are not completely black. Over very long periods of time, they can emit radiation. This is now known as Hawking radiation. The idea comes from considering quantum effects near the event horizon. In quantum physics, empty space isn't truly empty. It's filled with fluctuations, pairs of particles and antiparticles that briefly appear and then annihilate each other. Near the event horizon, something slightly different can happen. If one particle of such a pair falls into the black hole while the other escapes, the escaping particle becomes real, carrying away energy. From the outside, it looks as though the black hole is emitting radiation, and over time this process causes the black hole to lose mass, very slowly, extremely slowly for large black holes, but steadily. Now, for something like a stellar mass black hole, or even a supermassive one, this process takes an incredibly long time, much longer than the current age of the universe, so it's not something we can observe directly in action. But the theory suggests that, given enough time, a black hole could eventually evaporate, not suddenly, not explosively, but gradually shrinking as it loses energy. And that raises an interesting possibility. If black holes can lose mass and eventually disappear, then they're not permanent. They're part of a process, a very long one, but still a process. Now, this leads directly into the question we touched on earlier. What happens to the information? If matter falls into a black hole, carrying information about its structure, its composition, its history, and the black hole eventually evaporates, where does that information go? Is it lost? Does it somehow come back out, encoded in the radiation? Or does it remain in a form we don't yet understand? This is the black hole information paradox, and it's not just a small detail, it's a fundamental issue, because in quantum mechanics, information is not supposed to be destroyed. The laws of physics as we understand them preserve information, so if black holes truly erase it, that would suggest something is missing from our current theories. Over the years, many ideas have been proposed to resolve this. Some suggest that the information is encoded on the event horizon itself, in a kind of surface description. This is related to the holographic principle, which proposes that the information contained within a volume of space can be described by information on its boundary. Others suggest that the information is somehow carried away in the Hawking radiation, though in a very subtle and complex way. And there are even more speculative ideas involving connections between black holes and other regions of space-time. But so far, there's no single fully accepted answer. Now, stepping back from the technical details, there's a broader perspective to consider. Black holes may look like endpoints from the outside, but they're also part of a larger cycle. Stars form, live, and collapse. Black holes form from those collapses. They can grow by pulling in matter. They can merge with other black holes, and over extremely long timescales, they may even evaporate. So instead of a final stop, they might be better thought of as a phase, a stage in the ongoing evolution of matter and energy in the universe. Now, there's also another angle to this. Some theoretical ideas suggest that black holes could be connected to other structures. Wormholes, for example, are solutions to the equations of general relativity that connect two different regions of space-time. In some interpretations, a black hole could be linked to a white hole, a hypothetical object that expels matter instead of absorbing it. But these ideas remain speculative. There's no observational evidence that such connections exist in a way that would allow matter or information to pass through in a useful or stable manner. Still, they show that the concept of a black hole is not necessarily as simple as a one-way sink. It's part of a broader set of possibilities. Now, even without those more speculative ideas, there's something interesting about the way black holes interact with their surroundings. When they feed, they don't just consume, they release energy, they produce radiation, they can influence star formation, heat surrounding gas, and shape the structure of galaxies. So even as they pull matter inward, they're also contributing to the larger environment, and when they merge, they release energy in the form of gravitational waves, ripples that carry information across the universe. So in a sense, black holes are both absorbers and emitters. Not in the same way, not symmetrically, but part of a flow. Now, if you return to that original idea that black holes are the end, it starts to feel less complete. They're not the end in the sense of everything stopping. They're part of a process that continues, even if we can't see all of it. A transformation, a stage, and perhaps in ways we don't yet fully understand, a connection to deeper aspects of the universe. Now, as we begin to bring things together, it's worth reflecting on how far this journey has taken us, from the smallest stellar remnants to the largest known black holes, from quiet objects drifting through space to bright quasars visible across billions of light years, from simple definitions to questions that reach the limits of our current understanding, and all of it centered around something that, at first glance, seems so simple, a region where gravity is strong enough that nothing escapes. And yet, from that simple definition, an entire landscape of ideas unfolds. Now, after moving through all of that, it's worth slowing things down again, not to summarize in a strict sense, and not to close things off completely, but just to sit for a moment with the ideas we've explored. Because when you step back from the details, from the numbers and the processes and the different types of black holes, what remains is something much simpler, a quiet recognition of scale. We began with something that sounded almost familiar, a black hole, a term you've probably heard many times before, and from there we moved outward, or perhaps inward depending on how you think about it, into a landscape that gradually became more extreme. Collapsed stars leaving behind dense remnants, massive objects at the centres of galaxies, shaping the motion of billions of stars, black holes so large they stretch beyond the scale of entire solar systems, others that grow quickly, appearing early in the universe before there's been much time for anything to develop, and then the more unusual ones, the ones that wander, the ones that move, the ones that don't sit neatly where we expect them to be. Along the way, we saw how these objects don't just exist in isolation, they interact, they merge, they influence their surroundings, they release energy, sometimes in ways that make them the brightest things we can observe, and sometimes they remain completely quiet, hidden unless something nearby reveals their presence. There's a kind of balance in that. Some black holes are loud, in the sense that they produce enormous amounts of radiation, visible across vast distances. Others are silent, detectable only through careful measurement and long observation. But they all follow the same underlying principles: gravity shaping space, motion guiding matter, time behaving in ways that are different from what we experience every day. Now, if you think back to the idea of the event horizon, that boundary we talked about, it's interesting how much of our understanding revolves around what we can't see. We observe the edges, we measure the effects, we build models. But the interior remains out of reach, and that creates a kind of contrast. On one side, There's everything we can observe, the light, the motion, the energy. On the other, there's a region where information doesn't return. And between those two, there's a boundary that defines the limit of our knowledge. But even with that limit, we've been able to learn a great deal. Not by crossing that boundary, but by studying everything around it. And that's something that extends beyond black holes. It's a pattern in how we understand the universe. We observe what we can. We infer what we can't. We test ideas, refine them, adjust them as new information becomes available. And gradually our picture becomes more detailed. Never complete, but always improving. Now, there's also something else worth noticing. Even though black holes are often described as destructive, as places where things disappear, they're also part of a larger cycle. Stars form, live, and collapse. Black holes form from those collapses. They grow, merge, and interact. They release energy, influence their surroundings, and possibly, over very long timescales, even fade away. So instead of being final endpoints, they're part of an ongoing process. A transformation that fits into the broader story of the universe. And that story doesn't have a clear beginning or end in the way we usually think about it. It's continuous, evolving, changing over time. Now, if you imagine yourself drifting through space, far from any star, far from any galaxy, just moving slowly through the darkness, the presence of a black hole wouldn't necessarily be obvious. There would be no glow, no visible structure, just emptiness, stretching in every direction. And yet, somewhere out there might be one. Silent, invisible, a region where space and time behave differently. You wouldn't know it was there unless something gave it away. A distant star moving in an unusual path, a brief flash of light from matter falling in, or a subtle bending of light from something behind it. Otherwise, it would remain hidden. And there's something almost calm about that. Despite everything we've discussed, the immense gravity, the extreme environments, the energetic processes, black holes are not constantly dramatic. Most of the time, they simply exist. Quietly, persistently, part of the structure of the universe. Now, as we reach this point, there's no need to draw a sharp conclusion, no final statement that wraps everything up neatly, because the subject itself doesn't really allow for that. There are still questions, still uncertainties, still areas where our understanding is incomplete, and that's part of what makes it interesting. So instead of ending, it's perhaps better to leave things slightly open, to let the ideas settle without forcing them into a final shape. You've moved through the smallest black holes, the largest ones, the brightest, the fastest growing, the wandering, the merging, the spinning. You've seen how they form, how they behave, and how they challenge our understanding, and now all of that can simply rest. If you happen to look up at the night sky later, you won't see a black hole. Not directly. You'll see stars, maybe a faint band of the Milky Way if the sky's dark enough. But somewhere in that direction, hidden behind dust and distance, there will be one, at the centre of the galaxy. Quiet, unseen, and part of the same universe you're sitting in now. So, for now, just let that thought drift for a moment. No need to hold on to it too tightly. Just something to keep in the background as everything gradually settles into stillness.